On the second day of October, a phenomenon of incredible swiftness traversed the Martian atmosphere. Stephen Burns, an enthusiastic amateur astronomer, observed this celestial event within the raw image data procured by NASA's Perseverance rover. He meticulously compiled a time-lapse sequence, condensing 9 minutes of observational material. Within this compilation, the object was undeniably visible, exhibiting a speed of 60 kilometers per second, a velocity conspicuously deviating from the typical movement of celestial bodies. However, the situation escalated in strangeness. Other individuals began scrutinizing the same photographic evidence and reported perceiving not one, but multiple entities. These multiple, rapidly traversing anomalies were reportedly present in the data from October the 3rd, accompanied by an enigmatic green luminescence that has thus far defied explanation. This specific observation was pre-scheduled by NASA. A fleet of Martian orbiting satellites was intended to capture the most intimate imagery ever acquired of an interstellar visitor. The Mars Express, boasting a camera capable of 30-kilometer resolution, alongside the ExoMars Trace Gas Orbiter, all directed their focus toward Oumuamua during its closest approach on October the 3rd. Subsequently, an unnerving silence ensued. No official photographs, no data dissemination, nothing at all. Concurrently, Harvard's Avi Loeb has published findings that have cast a palpable disquiet throughout the entire astronomical community. This object, oumuamua, could potentially be the source of the legendary 1977 WOW signal. The statistical probability of this being mere happenstance stands at a mere 0.6%. Yet, the connection to the WOW signal represents only the precipice of the enigma, as oumuamua is defying every established principle of cometary behavior. It is generating industrial-grade nickel alloys in the vacuum of space. Its tail is oriented in an anomalous direction. Its spectral signature is green, a color it should not exhibit. Furthermore, it adheres to a trajectory so precisely aligned with our planet that the statistical odds are astronomically improbable. Some are now positing it as the most substantial interstellar object ever catalogued. Others deem it an impossibility. The scientific community, specifically those in advanced research, are characterizing it as potentially artificial. Presently, it has receded behind the sun, rendering it invisible and concealed as it approaches its nearest point to our star. The critical question remains: what will transpire when it reemerges? Before delving deeper into this perplexing narrative, if you find this exploration captivating, please engage the like button and subscribe to ensure you do not miss forthcoming revelations. Share in the comments section your geographical location, the current time where you are, and your assessment as to whether we are witnessing a singular entity or a multitude. To contribute to the expansion of this community, kindly disseminate this information across platforms such as X, Facebook, Reddit, or your preferred messaging service. Your steadfast support is deeply appreciated. Chapter 1. An Unforeseen Multiplicity. Let us revisit October the 2nd. Stephen Burns harbored no expectation of encountering anything extraordinary. His endeavor was simply the meticulous processing of the raw photographic data that NASA makes freely accessible from the Perseverance rover. The rover had been specifically tasked with observing the night sky during a designated interval, coinciding with the predicted closest proximity of Oumuamua to Mars. It is important to note that closest is a relative term in this context, referring to a separation of approximately 29 million kilometers. Burns captured a series of 9 consecutive images, which he then synthesized into a dynamic animation. In the realm of astrophotography, this technique serves to reveal movements that would otherwise remain imperceptible within a solitary frame. The stars, due to the rotational motion of Mars, appear to shift across the field of view. However, this instance presented a stark deviation. An object was traversing this established stellar progression at an angle that defied conventional celestial mechanics. Its velocity constituted the initial indicator of its unusual nature. At 60 kilometers per second, Oumuamua exhibits a speed exceeding that of almost any other known object within our solar system. For comparative purposes, Earth's orbital velocity around the Sun is approximately 30 kilometers per second. The Parker Solar Probe, humanity's swiftest spacecraft, achieves a velocity of 192 kilometers per second, and only during its closest solar approach. Yet, Oumuamua sustains this extraordinary pace throughout its transit. Burns disseminated his animation publicly. Within mere hours, fellow amateur astronomers commenced their independent analyses. It was then that an individual, identified by the username Nactaf, a German moniker translating to night monkey, put forth an assertion that sent reverberations through the observational community. In the images captured on October the 3rd, Nactaf asserted, you can even discern multiple comets. Not a single entity, but several. Another contributor, Alexander Fum, brought attention to an additional peculiarity. What is that flash at the 3-second mark? highlighted in green. A frame-by-frame review of Burns's animation reveals, at the precise 3-second interval, a fleeting emission of green luminosity. This phenomenon is neither a photographic artifact nor a cosmic ray impact, which would manifest as a single, intensely bright pixel. Instead, it presents as a diffuse glow, localized yet distinctly observable. The presence of green light in the cosmic environment is typically attributable to specific causes. On Earth, we associate it with auroras, with the combustion of copper, or with certain bioluminescent organisms. In space, green emissions usually originate from oxygen or from a molecular compound known as dicarbon, consisting of 2 bonded carbon atoms. Comets occasionally exhibit a green hue when solar radiation excites dicarbon within their comas. However, a significant discrepancy arises here. Spectroscopic analysis of oumuamua conducted by the Very Large Telescope indicated a virtual absence of dicarbon. The object is what astronomers categorize as depleted in carbon, and thus, it should not be emitting a green luminescence. Despite this, photographic evidence from ground-based telescopes acquired in early September clearly depicts a developing green aura surrounding the object. The green flash observed in the Martian imagery, if indeed genuine, further compounds the mystery. Regarding the purported multiple entities, this is where conjecture becomes a factor, albeit conjecture grounded in the analyses of individuals equipped with telescopes and sophisticated image processing software, rather than mere fabrication. When the stellar field within Burns's animation is stabilized, accounting for Mars's rotation and the movement of the primary object, at least 1 or 2 additional points of light emerge, displaying distinct velocities. Could these be artifacts of the imaging process? It is entirely possible. Could they be background asteroids that coincidentally appear within the frame? That too is a possibility. Or could they represent separate fragments or even smaller celestial bodies accompanying oumuamua? This is the central question for which no definitive answer is currently available, primarily because NASA has not yet released the comprehensive data. The Mars Reconnaissance Orbiter's high-rise camera documented oumuamua on October the 2nd, between the hours of 1 and 4 in the morning, Mars local time. The European Space Agency's Trace Gas Orbiter and Mars Express also recorded observations on October the 3rd. These were not casual captures. They were meticulously planned scientific endeavors designed to acquire the highest resolution data ever obtained of an interstellar object. The high-resolution imaging science experiment, HiRISE, instrument is capable of discerning features as minute as 30 centimeters on the Martian surface from orbit. When directed at an object situated 29 million kilometers away, it is expected to achieve a resolution of approximately 30 kilometers per pixel. Consequently, if oumuamua possesses a nucleus measuring 5 kilometers across, as recent estimates suggest, it should be rendered as a luminous cluster of pixels in the HiRISE imagery. More critically, HiRISE would be instrumental in differentiating between a singular, consolidated nucleus and a fragmented or multi-component structure. Should there be multiple constituent parts, a companion object, or any structural anomaly, HiRISE would undoubtedly document it. So where are the images? NASA's official pronouncements have been conspicuously concise. The Martian orbiters successfully completed their observational tasks. The data is currently undergoing processing. Updates will be provided as the analysis progresses. This statement was issued over 24 hours ago. In the context of space imaging, a 24-hour period is ample time to provide at least a preliminary review of raw data. Some observers have noted that the United States government is experiencing various administrative challenges that have impacted the release of scientific data. However, the European Space Agency operates independently and should be subject to no such impediments. Yet, the imagery from the ESA has also yet to surface. This prolonged silence feels deliberate, and when official channels fall silent, the amateur observer community invariably begins to voice its speculations. Because here is what we know with absolute certainty. The Perseverance rover did indeed capture something. Multiple amateur analysts, examining the same publicly accessible raw data, are identifying anomalies. The observed object or objects are moving at velocities consistent with oumuamua. And then there is that inexplicable green flash. What remains unknown is whether these apparent multiple entities are verifiably real, whether they are distinct from the primary celestial body, and what precisely NASA and the ESA discerned with their significantly more powerful instruments. The flyby on October the 3rd represented the closest encounter any spacecraft has ever achieved with an active interstellar object. This was our prime opportunity to ascertain the true nature of oumuamua, to examine its structure at close range, and to determine whether its behavior aligns with that of a conventional comet or something entirely different. And as we await these crucial answers, the object itself continues its cosmic journey. It is currently approaching the Sun, venturing deeper into the inner solar system, where Earth-based telescopes lose their observational capacity due to the intense solar glare. By the conclusion of October, it will transit behind our star from our vantage point, rendering it entirely invisible. Upon its reappearance in November or December, it will either validate every conceivable natural explanation or it will have performed an action utterly alien to the behavior of comets. However, before its final disappearance from view, it is imperative to discuss the true objective of the Martian observations and why the timing of this data blackout is more significant than one might initially assume. Chapter 2. The Martian Data Blackout. There exists a discernible pattern in the manner in which space agencies handle sensitive observational data. When routine phenomena are documented, the corresponding data is typically made available within hours. Raw imagery populates public repositories, and press releases are promptly issued. Scientists frequently share their initial findings via social media. Conversely, when unexpected events are detected, a period of extended silence ensues. The technical justification often cited for such delays pertains to data processing pipelines and calibration protocols. Martian orbiters do not transmit imagery in real time. Instead, they store their observations on board and then beam them to Earth during scheduled communication windows. Subsequently, the data undergoes a series of processing stages, including geometric correction, radiometric calibration, and noise filtering. For a standard surface observation, this entire procedure typically spans between 6 and 12 hours. For a moving target observed against a starfield, this duration may extend to twice that length. We are presently well beyond the 48-hour mark since the observations conducted on October the 3rd. However, another factor is at play, one that is rarely mentioned in official statements but circulates within the research community that relies on NASA's data for their work. Budgetary constraints and administrative disruptions have created bottlenecks within data release protocols. This is not a formal shutdown, but rather a form of bureaucratic friction that transforms routine procedures into protracted ones. Staff may be working reduced hours, priority systems might be reallocated, and review chains can become considerably longer. The European Space Agency, operating under different administrative structures, has also not yet released the imagery from its Mars Express and ExoMars Trace Gas Orbiter missions. This suggests either a coordinated decision to withhold preliminary data until a comprehensive analysis is finalized or the presence of technical challenges that both agencies are concurrently addressing. The pertinent question then becomes, what could be sufficiently challenging to necessitate such a delay? Consider the intended capabilities of these instruments. The Color and Stereo Surface Imaging System, CASIS, aboard the Trace Gas Orbiter can resolve features down to approximately 4.5 meters per pixel when imaging Mars. However, when pointed at an object 29 million kilometers distant, this resolution diminishes significantly, though the instrument's sensitivity remains high. It is designed to detect subtle variations in the color of Martian surface materials. If oumuamua were emitting multiple types of ice, if its coma displayed compositional heterogeneity, or if it possessed structurally distinct regions, CASIS would undoubtedly capture such details. Mars Express is equipped with the high-resolution stereo camera, which, despite its name, primarily focuses on three-dimensional topography. For a distant comet, its stereo capability becomes less critical than its capacity to image across multiple wavelengths simultaneously. This camera can differentiate between dust, water ice, carbon dioxide ice, and various minerals based on their distinct reflectivity across different wavelengths of light. Then there is the High-Resolution Imaging Science Experiment, HiRISE, camera on the Mars Reconnaissance Orbiter, which we have previously mentioned. However, an important aspect we have not yet discussed is that HiRISE does not merely capture photographs. It collects data across three distinct color bands: blue, green, red, and near-infrared. When directed at a comet, these bands reveal different facets of its composition and activity. Blue-green light interacts with the gases present in the coma, while red and near-infrared light penetrate through thinner dust layers, exposing underlying structures. If the comet were ejecting material in jets from specific points on its nucleus, if these jets possessed varying compositions, or if the object's brightness fluctuated in a manner suggesting a non-uniform surface, HiRISE would meticulously document all such characteristics. The critical point concerning sensitive imagery is that it can sometimes reveal features that necessitate consultation and verification before public release, not due to any conspiracy, but because preliminary observations can be susceptible to misinterpretation without proper context. If HiRISE captured an unusual feature, mission scientists would prioritize ruling out instrumental artifacts, cosmic ray impacts, or processing errors before making the data accessible to the public. However, while we await the official channels to open, there is Simeon Schmaus. Schmaus is an astrophotographer renowned for his expertise in processing raw planetary data. He is recognized within the community for his proficiency in extracting signals from noisy images, stabilizing shaky video footage, and accentuating subtle features that might be overlooked in initial processing. On October the 1st, a day prior to Stephen Burns's time-lapse capture on October the 2nd, Perseverance acquired a series of night sky images. These were promptly uploaded to NASA's raw image database, as is customary for all Perseverance imagery, within hours of their reception on Earth. Schmaus downloaded these images, applied his specialized processing techniques, and claimed to have obtained an early glimpse of oumuamua within those frames. This assertion has not yet been independently verified. Given its distance and angle at that time, the object would have been exceptionally faint, but if legitimate, it would indicate that the comet was detectable even before the primary observation window. More intriguingly, Schmaus observed that the trajectory he detected did not perfectly align with the predicted path. It showed a slight deviation. He publicized his findings on social media, noting that further analysis was required but deeming the preliminary results highly compelling. Subsequently, much like the official sources, he ceased making public statements. Whether he is still engaged in analysis, whether he has uncovered something he wishes to confirm before further discussion, or whether he has been requested to refrain from comment, remains unknown. What is evident is the existence of a temporal gap, a void between the expected routine disclosure and the current reality. A void exists between the scheduled observations and the data available for public examination. This void is currently filled with amateur discoveries, unexplained green flashes, and claims of multiple entities that neither official channels can definitively confirm nor deny. The Perseverance rover continues its surface mission, its cameras remain fully operational, and its data continues to be uploaded to the public database. However, the specific imagery from those pivotal nights, the ones holding the greatest significance, are the very images being subjected to scrutiny in a hushed and prolonged silence. By October the 29th, oumuamua will reach perihelion, its point of closest approach to the Sun. At this juncture, from Earth's perspective, it will be positioned directly behind our star, rendering it invisible to both ground-based and space-based observatories. The window for observation is rapidly diminishing. Whatever NASA and the ESA have observed, whatever Schmaus has discovered, whatever is unfolding behind the review processes and data pipelines, the clock is undeniably ticking. Because if there is indeed something unusual about this object, if those multiple points of light are more than mere illusion, if the green flash signifies something profound, we must ascertain these facts before it recedes into the blinding solar glare. And if these answers remain elusive, we will be compelled to wait until November, when the comet reemerges on the opposing side, potentially transformed by its close solar encounter, potentially having exhibited behavior that defies the norms of natural comets. However, there is an additional rationale behind the significance of this timing. While our attention has been captivated by the potential revelations from the Martian observations, Loeb has been meticulously tracing oumuamua's path, not merely through our solar system, but backward through time. And his findings establish a compelling link between this object and one of the most iconic unexplained signals in the annals of astronomical history. Chapter 3. The WOW Signal Revelation. On August the 15th, 1977, Ohio State University's Big Ear radio telescope was engaged in a routine celestial survey, specifically searching for signals that might indicate the presence of technological civilizations beyond Earth. The telescope operated autonomously, scanning narrow segments of radio frequencies and recording intensity readings on continuous paper. It was 3 days later, while reviewing these printouts, that astronomer Jerry Emmon noticed something that prompted him to reach for a red pen. A signal had appeared, powerful and narrowband, lasting precisely 72 seconds. The intensity of this signal far surpassed the background noise, leading Emmon to circle the alphanumeric sequence and annotate the margin with a single word. Wow! The signal originated from the direction of Sagittarius, in proximity to the globular cluster M55. It was detected at a frequency of 1,420 MHz, a frequency situated within the protected radio astronomy band. No human transmissions are permitted at this specific frequency. The signal's bandwidth was narrow, less than 10 kHz, precisely the characteristic expected from an artificial transmitter rather than a natural astronomical source. The Big Ear telescope never detected this signal again. Subsequent observational attempts yielded no results. For nearly 50 years, the WOW signal has remained one of astronomy's most profound enigmas, until Loeb undertook the calculation of oumuamua's position on that historical date. By extrapolating backward from the object's current trajectory and velocity, Loeb charted its path through space. In August of 1977, oumuamua would have been approximately 600 astronomical units from Earth. This distance is 600 times the separation between Earth and the Sun, placing it in the distant outer reaches of the solar system. though not yet in true interstellar space. The WOW signal emanated from celestial coordinates corresponding to a right ascension of 19 hours 25 minutes and a declination of -27 degrees. These coordinates point toward the constellation Sagittarius. Loeb calculated Oumuamua's position on August 15, 1977. At that time, the object would have been at a right ascension of 19 hours 21 minutes and a declination of -19 degrees. This represents a separation of 4 degrees in right ascension and 8 degrees in declination. In astronomical terms, this alignment is remarkably precise. The probability of two random celestial directions aligning within 9 degrees of each other is approximately 0.6%. However, mere alignment does not establish causality. Loeb proceeded further. If Oumuamua were the source of the WOW signal, what would have been the requisite power output of its transmitter? The signal intensity detected by the Big Ear ranged from 54 to 212 Janskis. A Jansky serves as a unit of measurement for radio flux density. For comparative context, the most powerful radio sources in the sky, such as the Sun or Jupiter, typically register in the hundreds to thousands of Janskis when observed at specific frequencies. At a distance of 600 astronomical units, generating the observed signal intensity would necessitate a transmitter outputting between half a gigawatt and 2 gigawatts of power. This power output range is comparable to that of a typical nuclear power reactor on Earth. While not an insurmountable technological feat, nor even particularly advanced for a civilization capable of interstellar travel, it is noteworthy because it aligns precisely with the kind of power budget that would be sensible for a deep space probe attempting to communicate across vast cosmic distances. There is an additional detail of significance. The WOW signal exhibited a slight frequency shift. It was detected at 1420.4556 MHz, which is approximately 10 kHz higher than the frequency of the neutral hydrogen line. This indicates a blue shift, signifying that the source was moving toward Earth. Oumuamua is currently approaching the Sun at an approximate velocity of 60 kilometers per second. When one accounts for Earth's motion and its geometric orientation in August of 1977, the resultant relative velocity would indeed produce a blue shift. Loeb calculated the expected shift, which closely approximates the observed value, though not a perfect match. This discrepancy could be attributed to uncertainties in the precise positional and velocity vectors, or to the signal having been transmitted in a specific direction rather than omnidirectionally. From a strategic perspective, here is where the scenario becomes particularly intriguing. If an intelligent extraterrestrial entity intended to announce its presence, broadcasting near the hydrogen line would be a logical choice. Hydrogen is the most abundant element in the universe, and the 21-centimeter hydrogen line is so fundamental to radio astronomy that any civilization possessing radio technology would inevitably monitor it. It effectively serves as a universal galactic calling card frequency. The WOW signal's 72-second duration stemmed from the operational mechanics of the Big Ear radio telescope. This instrument employed two spatially separated feed horns that scanned adjacent celestial zones as Earth's rotation swept them across the intended target. Each feed horn possessed a receptive window of 36 seconds. The extraterrestrial signal registered within both horns sequentially, thereby establishing the total 72-second observation period. This phenomenon implies the source was either continuously broadcasting or transmitting for the entire interval during which Big Ear could detect it, suggesting a sustained transmission rather than a fleeting pulse. If 3 Atlas were indeed the source, this immediately prompts several perplexing questions. Was it a beacon intended to announce its presence to any listening entity? Could it have been a navigational signal, marking a position for other celestial craft? Or was it an attempt at direct communication, encoding information beyond our current decoding capabilities? Alternatively, could it be entirely coincidental, a cosmic fluke where an interstellar comet happened to align with an unidentified natural radio source? The fundamental issue is the absence of radio telescope data pertaining to 3 Atlas. Not only is there no data from August 1977, but there is also no contemporary data. No astronomical observatory has reported directing radio dishes towards this object. The focus has predominantly been on optical observations, including spectroscopy and imaging, with inquiries centering on its composition and structure, not its potential for transmission. Avi Loeb asserts that this investigative approach must be reassessed promptly. The celestial body is approaching its perihelion, drawing closer to the Sun, which will result in elevated temperatures and increased activity. This scenario implies greater energy availability, should any form of technological system be involved. If it transmitted a signal from 600 astronomical units away, and if its design involves communication at specific junctures of its trajectory, then this present moment is opportune. Radio observatories, such as the Very Large Array in New Mexico, successor facilities to Arecibo, and the extensive arrays in China and Australia possess the capability to monitor 3 Atlas across a broad spectrum of frequencies, extending beyond the hydrogen line to encompass frequencies where artificial signals might manifest. The observation process would be straightforward: direct the instruments, listen intently, and compare the readings against background noise. The objective would be to identify any narrowband signals, modulation patterns, or repetitive structures that deviate from those produced by natural celestial sources. If nothing is detected, it would simply confirm the current understanding, requiring only a few hours of telescope time to dismiss this hypothesis. However, if any signal is detected, even faint or intermittent radio emissions from 3 Atlas, it would fundamentally alter our interpretation of this object. This is because comets, defined as chunks of ice and rock, even those originating from other star systems, do not spontaneously generate radio signals at specific frequencies. While natural astronomical phenomena do produce radio emissions, these are typically broadband, chaotic, and lack the discernible structure indicative of intentionality. The WOW signal, conversely, exhibited structure, a narrow bandwidth, and appeared at a statistically significant frequency. If Avi Loeb's hypothesis regarding the alignment holds true, transforming a 0.6% coincidence into a causal link, then approximately 48 years ago, somewhere within the outer reaches of our solar system, an entity transmitted a signal of sufficient power to be detected. This entity is now traversing the vicinity of Mars, obscured from our view by the Sun, exhibiting behaviors inconsistent with those of a typical comet. The critical question is not whether we should be listening, but rather why we are not already doing so. Chapter 4 delves into the possibility of manufactured alloys originating in space. As comets approach the Sun, they begin to expel material from their surfaces. This process involves the direct sublimation of ice from a solid to a gaseous state, the liberation of dust particles, and the release of trapped volatiles. On occasion, when a comet reaches a sufficiently high temperature, trace amounts of metals can vaporize from embedded dust grains. Nickel and iron are consistently observed together in these outgassing plumes, a phenomenon attributable to their co-formation during stellar processes, their presence together in meteoritic material, and their similar sublimation temperatures. While the ratio of these elements can vary slightly between comets, it generally adheres to a predictable pattern. For every atom of nickel detected, approximately 10 atoms of iron are expected. The prior interstellar comet, 24/Boros, conformed precisely to this rule, as do comets within our solar system and other icy bodies exhibiting metal emissions. The sole exception to this pattern is 3 Atlas. The European Very Large Telescope, situated in Chile, has been scrutinizing this object using its ultraviolet and visual spectrograph, an instrument engineered for exceptionally precise light dispersion into its constituent wavelengths. During the period between August and September, observers captured spectroscopic data across 6 distinct time intervals as the comet traversed from 3.14 astronomical units to 2.14 astronomical units from the Sun. In every observational window, nickel emission lines were evident within the spectrum, appearing bright, clear, and unmistakable. Iron, however, was only detected when the comet drew closer than 2.64 astronomical units. Prior to this threshold, nickel was observed without iron. Subsequently, nickel appeared alongside some iron, but in ratios markedly divergent from anything observed in other comets. The measured nickel-to-iron ratio was orders of magnitude higher than solar abundance ratios, exceeding typical cometary ratios and far beyond what natural geological processes would produce. The rate of production further compounded the strangeness of these findings. 3 Atlas was expelling nickel gas at an estimated rate of 5 grams per second upon its initial observation. As it approached the Sun and its temperature increased, this rate escalated dramatically. 5 grams per second may seem insignificant, but when extrapolated, it translates to approximately 430 kilograms per day, or over 3 tons of nickel per week, emanating from an object presumed to be composed primarily of water ice and rock. The surface temperature at 2.8 astronomical units, the location where much of this emission was observed, is far too low to vaporize silicate minerals or metallic grains containing nickel and iron. The comet would need to be at least twice as close to the Sun for conventional sublimation of refractory materials to occur. This strongly suggests an alternative process is at play. The research team has posited several potential explanations. One possibility is that nickel exists in a readily releasable form, such as nickel tetracarbonyl, a volatile compound that decomposes under ultraviolet light, releasing free nickel atoms into the coma. However, the formation of nickel tetracarbonyl necessitates specific chemical conditions and pathways that are not commonly encountered in natural processes. On Earth, nickel tetracarbonyl is synthesized industrially as part of the Mond process for purifying nickel from ore. This involves heating impure nickel with carbon monoxide under specific temperatures and pressures, forming gaseous nickel carbonyl, which is then decomposed at higher temperatures to deposit pure nickel. The chemical signature observed with 3 Atlas, the release of nickel unaccompanied by corresponding iron, mirrors the output of this industrial refining procedure. Another possibility mentioned by the researchers is that the nickel is embedded within organic compounds or exists as nanoscale particles, which respond differently to solar heating compared to bulk metal grains. Alternatively, photon-stimulated desorption, where light directly ejects atoms from the surface, might preferentially release nickel. While these are plausible natural mechanisms, they are complex and contingent upon specific conditions, yet still conceivable. However, natural mechanisms typically leave discernible evidence and require precursor materials, reflecting the comet's formation history, its interstellar journey, and its exposure to radiation. 3 Atlas likely originated in the Milky Way's thick disk, a region characterized by older, metal-poor stars. Models suggest it spent between 4 and 7 billion years traversing interstellar space before entering our solar system. During this extensive voyage, it would have been subjected to cosmic rays, background radiation, and collisions with interstellar dust and gas. Could this exposure have fostered surface chemistry exotic enough to account for the nickel emissions? Is it possible that the comet accumulated material during its journey that, upon being heated by the sun, releases metals in unusual ratios? It is reasonable to expect that comets formed around different stars would exhibit chemical variations, as protoplanetary disks possess distinct compositions. The elemental mix, the ratio of volatile to refractory materials, and the structure of organic molecules all vary depending on the location and epoch of solar system formation. Nevertheless, the fundamental laws of physics remain constant. Nickel and iron still co-form in supernovae, condense together in protoplanetary disks, and sublimate at similar temperatures. Achieving their separation and release in dramatically different ratios would require overcoming fundamental chemical relationships. This scenario is plausible only if the nickel is not sublimating from ice and rock, but rather is being released through a process involving chemistry not typically associated with comets. Avi Loeb has astutely pointed out that the observed phenomena align with expectations for artificial nickel production. This does not imply the comet itself is a manufacturing facility, but rather that if it were a technological artifact with nickel-based components or a nickel-rich surface coating acquired during interstellar travel, solar heating could ablate such material. The absence of iron would then simply reflect the composition of the eroded substance. The counterargument to this proposition is straightforward. Why would an advanced civilization construct an object from materials that readily vaporize? Designing an interstellar probe intended to endure for billions of years would likely eschew materials that begin to vaporize upon proximity to a star. This is unless the vaporization is intentional, serving a specific purpose such as cooling, mass shedding for trajectory adjustment, signal generation, or the creation of a visible marker observable from afar. Alternatively, the accumulated coating during the journey might not have been part of the original design. Interstellar space is not a void. At velocities of 60 kilometers per second, even diffuse gas and dust particles impact with considerable energy. Over millions of years, a spacecraft would accumulate surface material, much like a comet. If this accreted material happened to be rich in certain elements, depending on the galactic regions traversed, unusual compositions could arise. The data from the Very Large Telescope does not provide definitive proof of these hypotheses. It merely establishes that 3 Atlas is exhibiting anomalous behavior. The presence of nickel without iron, the extreme production rates, and the timing of the appearance of different emissions do not align comfortably with our established models of cometary behavior. And nickel is merely one facet of this enigma. While the VLT was documenting metallic emissions, the Hubble Space Telescope was capturing images revealing something even more fundamental, something that challenges the very definition of a comet. Chapter 5 introduces the phenomenon of the anti-tail anomaly. Comet tails characteristically point away from the sun. This is a fundamental characteristic, driven not by the comet's motion, but by the outward pressure exerted by solar radiation and the solar wind. Photons carry momentum, and when billions of them strike dust particles and ionized gas molecules each second, they transfer this momentum, creating the iconic tail that invariably streams away from the sun. The directionality of this tail is so integral to cometary behavior that astronomers can ascertain the sun's location simply by observing the tail's orientation. On July 21st, the Hubble Space Telescope acquired its highest resolution image to date of 3 Atlas. At that time, the comet was 277 million miles from Earth, still inbound towards its perihelion in October. The image depicts a diffuse luminescence situated ahead of the object, directed towards the sun. This luminescence is elongated, roughly 10 times longer than it is wide, forming a structure resembling a teardrop or a jet. Behind the object, in the direction where a tail would normally trail, there is an absence of any significant plume or extended dust trail, only a faint gradient of scattered light diminishing into the darkness of the background. This forward glow is identified as an anti-tail. While anti-tails are not entirely unknown in comets within our solar system, their occurrence is typically attributed to specific geometric conditions. When Earth passes through a comet's orbital plane, dust particles left behind in the comet's orbit can, from our perspective, stretch out in front of the comet, creating an optical illusion. However, 3 Atlas is not situated within such a geometric configuration. The viewing angle does not support a perspective-based effect, and the brightness profile of the forward glow does not conform to what would be expected from orbital dust. David Jewett, an astronomer at UCLA who led the Hubble observations, analyzed the surface brightness as a function of distance from the nucleus. In a typical cometary coma, brightness diminishes gradually as dust disperses and dilutes, with intensity decreasing according to a gentle power law. The forward glow of 3 Atlas, however, exhibits a steep decline, with a projected power law slope of -3, corresponding to a 3-dimensional emissivity profile with a radial slope of -4. This gradient is considerably steeper than observed in most solar system comets. Such a steep falloff suggests that the source of the glow is concentrated near its origin and dissipates rapidly. This could be due to either extremely fine-grained material being quickly dispersed by radiation pressure or active jetting from a specific point on the nucleus, creating a directed plume. Jewett's team interpreted this phenomenon as dust evaporating from the sunward side of the comet. Solar heating would be most intense on the hemisphere facing the sun, leading to ice sublimation and dust release. This dust cloud would expand forward before radiation pressure begins to push it backward. While this is a plausible interpretation, it necessitates an asymmetrical shedding of material, with the sunward side being dramatically more active than the rest of the surface, a level of asymmetry that, while unusual, is not impossible. What proves more challenging to explain is the absence of a dust tail. If dust is being ejected from the surface in quantities sufficient to generate the visible forward glow, this dust should persist. Radiation pressure would propel it outward, and the comet's motion would draw it into a tail, which we should observe. One possibility is that the dust particles are exceptionally small. Particles less than a few hundred nanometers interact so strongly with light that they are rapidly blown away from the comet, forming a faint haze rather than a distinct tail. However, such minute particles are also quickly destroyed by solar radiation, breaking down into even smaller fragments until they become essentially invisible. Another possibility is that a significant portion of what we are observing is not dust but gas. Gas does not form persistent tails in the same manner as dust. It disperses, thins, and becomes transparent as it moves away from the nucleus. If gas is the primary component of the forward glow, this brings us back to questions of composition and the rate of gas expulsion. Furthermore, why would it be so concentrated in one direction? An alternative hypothesis explored by Loeb and his colleague Eric Keto suggests that if 3 Atlas is generating its own light rather than merely reflecting sunlight, the brightness profile would differ. Internal energy sources, whether from radioactive decay or other processes, would produce emission that diminishes rapidly with distance, simply due to the increasing separation from the source. This concept is not entirely speculative. Some comets exhibit faint air glow within their comas, resulting from molecules excited by solar ultraviolet light. However, these emissions are well characterized, with predictable wavelengths, intensities, and structures. The Hubble image captures broadband light across a range of wavelengths. Without spectroscopic analysis of the specific forward glow, it remains difficult to ascertain whether it is solely reflected sunlight or includes an emission component. What is clear is that the observed structure is anomalous, forward-directed, exhibiting a steep falloff in brightness, and lacking a corresponding tail. These combined features present a scenario that deviates from standard cometary models, requiring the invocation of extraordinary circumstances. The significance of this lies in the orientation of this jet, plume, or whatever designation is applied. It points in the direction of the comet's motion. As the comet travels toward the sun, the glow extends ahead of it in the same direction. If one were designing a braking system for an interstellar object, releasing material forward would generate thrust in the opposite direction. While not as efficient as rocket propulsion, over extended periods and with continuous mass loss, it could induce measurable deceleration. 3 Atlas has exhibited no measurable non-gravitational acceleration. Multiple research teams have analyzed its trajectory, compiling thousands of positional observations, and have found its motion to be consistent with gravitational forces alone. However, this analysis has limitations. Small accelerations, below approximately 15 meters per day squared, would be obscured by observational noise, and the observation window is relatively brief. The comet was only discovered in July, and we have tracked it for a few months across a segment of its orbit. If it were undergoing slow deceleration, gradually adjusting its trajectory through directed mass loss, it might not yet be detectable. Alternatively, the forward jet could be entirely natural, a consequence of how ice sublimates from a rapidly rotating nucleus with an irregular shape. The image alone cannot definitively answer this question. However, when considered in conjunction with other anomalies, the nickel emissions, the chemical composition, and the trajectory, it contributes to a pattern where each individual observation can be explained through natural phenomena. Yet, the collective picture strains credulity. It is possible to encounter a comet with unusual chemistry, one with an atypical trajectory, or one that outgasses asymmetrically. However, the confluence of all these features in a single object, the third interstellar visitor ever detected, begins to push the boundaries of statistical probability, particularly when one considers the sheer mass of this object. Chapter 6 addresses the mystery of 33 billion tons. When an active comet expels gas and dust, the principles of physics dictate a reaction, action, and reaction. Material ejected from the surface generates thrust, albeit a small but measurable amount. A typical comet might experience non-gravitational acceleration in the range of a few hundred meters per day squared, over weeks and months. This causes the trajectory to deviate from a purely gravitational path. Astronomers utilize these deviations to estimate the amount of mass a comet is losing, and by extension, the mass of its nucleus. More massive objects exhibit greater resistance to acceleration. A small nucleus-shedding material will deviate noticeably, whereas a large one will barely budge. Between May 15th and September 23rd, 227 observatories worldwide tracked 3 Atlas. More than 4,000 individual positional measurements were compiled at the Minor Planet Center, the international clearinghouse for small body observations. Richard CLU, Peter VE, and Avi Loeb analyzed this dataset. They fitted the observations to a purely gravitational trajectory, calculating the comet's expected position at each moment based solely on the sun's gravity and planetary perturbations. Subsequently, they examined the deviations. The upper limit established for non-gravitational acceleration was less than 15 meters per day squared, potentially significantly less, perhaps even zero, but definitively below that threshold. This is astonishingly low for an active comet that is visibly outgassing. The James Webb Space Telescope detected carbon dioxide escaping from 3 Atlas at a rate of approximately 150 kilograms per second in early August, which equates to 13 tons per day. As the comet approached the sun through September, this rate likely increased. When mass is ejected at high velocity, the principle of conservation of momentum dictates that the remaining object experiences a force. The gas emanating from the surface has an outflow velocity of around 440 meters per second, as measured by Webb spectroscopy. Plugging these values into the calculation, multiplying the mass loss rate by the velocity, and dividing by the comet's mass, determines the expected acceleration of the comet. If 3 Atlas demonstrated negligible acceleration despite this continuous mass loss, its nucleus must possess a mass sufficient to render the thrust undetectable within the observational noise. The calculation yields a minimum estimated mass of 33 billion tons. Contemplate this magnitude. The initial visitor from beyond our solar system, designated oumuamua, possessed an estimated mass ranging from 10 million to 100 million tons, a figure dependent on suppositions regarding its density and form. The subsequent interstellar entity, 2I/Borisov, was estimated to weigh several hundred million to a few billion tons, inferred from its luminosity and observable activity. 3I/2017 U1, Suchinshin 1, also known as Atlas, registers a minimum mass of 33 billion tons, with the potential to be significantly more massive, as this figure represents a lower bound. It could plausibly be 10 times heavier while still conforming to observational data. This elevates its mass to a factor of 1,000 to 1,000,000 times greater than prior interstellar sojourners. This is where statistical analysis begins to yield disquieting results. Models describing the formation and expulsion of interstellar objects from planetary systems predict a specific size distribution. Smaller entities should vastly outnumber their larger counterparts. This is not an arbitrary conjecture. It is grounded in our understanding of planetary accretion, gravitational dynamics, and the mechanisms by which material is ejected from stellar systems. For every kilometer-sized object traversing interstellar space, there should exist thousands of objects measuring 100 meters across. Correspondingly, for every 100-meter object, there should be thousands more at 10 meters. This distribution adheres to a power law. When we first detected oumuamua, approximately 100 meters in size, this was precisely as anticipated. Small objects are commonplace. Their detection is more challenging due to their faintness, but with continuously scanning telescopes, their discovery is expected. 2I/Borisov, being larger and more active, aligned with this same predictive framework, exceeding oumuamua in size, but remaining within the anticipated range of encounters. 3I/Atlas fundamentally disrupts this pattern. Its minimum diameter, derived from the 33 billion ton mass estimate, surpasses 5 kilometers. More realistically, given our knowledge of cometary densities, it is likely between 5 and 10 kilometers in extent. Objects of such magnitude should be exceptionally rare. Current models suggest we should detect approximately 10,000 to 100,000 smaller interstellar objects before encountering one of this colossal size. To date, we have identified only 2. This phenomenon has been termed a major anomaly by some researchers. However, this term significantly understates the situation. If 3I/Atlas is indeed 5 kilometers or more across, and we are only now encountering it as the third identified interstellar object, then either our models for interstellar object populations are profoundly erroneous, or we have experienced an extraordinary stroke of luck, bordering on statistical impossibility. Or 3I/Atlas does not represent a random sample from the expected population. The luck hypothesis necessitates belief in encountering a 1 in 10,000 chance, or worse, a possibility, albeit an unsettling one. The wrong models hypothesis implies a need to reevaluate fundamental assumptions concerning planetary system formation and evolution, the ejection processes of objects into interstellar space, and the mass distribution of galactic debris. While not impossible, this would necessitate significant revisions to theories that have proven robust for all other astronomical observations. The non-random hypothesis proposes that 3I/Atlas is anomalous for reasons extending beyond mere statistical probability. It might have formed through a rare process that generates large objects with greater frequency than standard planet formation models predict. Perhaps it is a nascent planetary core, a large solid fragment ejected early in a star system's history, as some scientists have posited. Alternatively, it might be following a deliberate trajectory that brought it to our vicinity, rendering its detection a matter of design rather than serendipity. This latter proposition is what makes most astronomers uneasy, not because it is inherently impossible, but because embracing it would require abandoning the scientific tenet of exhausting natural explanations before invoking extraordinary ones. The prevailing dilemma lies in determining at what point natural explanations become more extraordinary than the alternative. A comet exhibiting a mass 1 million times greater than anticipated, displaying industrial metal signatures, expelling material forward without a discernible tail, glowing green without the requisite molecular compounds, aligning with a celebrated radio signal with a probability of less than 1%, and traversing a trajectory passing remarkably close to multiple planets. Each individual anomaly possesses a plausible natural explanation. However, their confluence strains credulity. Furthermore, we have yet to address the most perplexing aspect of its chemical composition, a discovery that garnered significant media attention precisely because it defied all established understanding of cometary constituents. Chapter 7. The Chemical Conundrum. On August 6th, the James Webb Space Telescope directed its near-infrared spectrograph toward 3I/Atlas. Operating above Earth's atmosphere, Webb is shielded from the atmospheric water vapor and carbon dioxide that impede ground-based infrared astronomy. Its instruments can detect molecules invisible to terrestrial telescopes. The spectroscopic analysis revealed the presence of carbon dioxide, water, carbon monoxide, and carbonyl sulfide within the comet's coma. These are all expected components of an active comet, but their relative proportions were profoundly anomalous. The ratio of carbon dioxide to water was measured at 8:1. In every other comet ever studied, including the preceding interstellar visitor 2I/Borisov, water is the dominant volatile. Carbon dioxide typically constitutes a minor component, generally comprising between 5 and 20% of the total volatile inventory. Water ice forms the bulk of cometary material due to the abundance of water in the protoplanetary disks where comets originate. 3I/Atlas completely inverts this ratio. For every molecule of water, there are 8 molecules of carbon dioxide. By mass fraction, the coma consists of approximately 87% carbon dioxide, 9% carbon monoxide, and merely 4% water. This ratio deviates from the typical value for solar system comets by 6 standard deviations. Statistically speaking, this represents not an outlier, but an entirely distinct population. Martin Cordiner, the astronomer leading the Webb observations, suggested that such a high concentration of carbon dioxide could indicate the comet formed near the carbon dioxide ice line in its parent protoplanetary disk. This is the region surrounding a young star where temperatures are sufficiently low for carbon dioxide to condense into solid ice. Within our solar system, this line is situated farther from the sun than the water-ice line. Objects forming between these two boundaries would indeed be rich in carbon dioxide, but even in such a scenario, water would be expected to be a significant component, not reduced to a mere 4%. Another potential explanation involves radiation processing. 3I/Atlas has spent billions of years traversing interstellar space, subjected to bombardment by cosmic rays. This radiation can alter surface chemistry, breaking down water ice molecules while leaving carbon dioxide relatively unaltered. Over extended periods, this could create a surface layer enriched in carbon dioxide, but this would be a surface phenomenon. As the comet approached the sun and began shedding material, one would expect to encounter more typical compositions beneath this processed layer. The spectroscopic data, however, shows no indication of such a transition. The carbon monoxide ratio introduces another puzzle, being approximately 1.4 times the abundance of water. While elevated, it is not as dramatically so as the carbon dioxide. Carbon monoxide is even more volatile than carbon dioxide, sublimating at lower temperatures. If the comet were simply warming and releasing ices in order of volatility, carbon monoxide should have appeared first and in high abundance. Instead, carbon dioxide dominates, with carbon monoxide as a secondary component and water lagging significantly behind. This chemical composition suggests formation conditions dissimilar to anything observed in our solar system. The comet either originates from a protoplanetary disk with a drastically different composition than the one that formed our planets, or it underwent transformative processes during its interstellar journey, altering its makeup into something entirely unprecedented. Furthermore, there is the matter of polarization. When light interacts with dust particles, it becomes polarized. The degree and orientation of this polarization are contingent upon the size, shape, and composition of the particles, as well as the viewing angle. Astronomers utilize polarization data to infer cometary dust properties that are difficult to measure directly. A research team headed by Zach Gray observed 3I/Atlas through polarizing filters over several weeks. They measured polarization as a function of phase angle, defined as the angle between the Sun, the comet, and Earth. The findings were unlike any object within our solar system. 3I/Atlas exhibited extreme negative polarization. At small phase angles, the polarized light was oriented perpendicularly to the polarization observed from all other comets, asteroids, and dusty celestial bodies. The magnitude of this negative polarization surpassed any recorded in the existing database. Negative polarization can occur when light is scattered by particles possessing specific optical properties. However, achieving the observed degree of polarization necessitates unusual combinations of size, composition, and structure. The dust grains would likely need to be larger than typical cometary dust, possibly with intricate internal structures or atypical refractive indices. Alternatively, the scattering mechanism might not align with our standard models. If the primary light source is not solely scattered sunlight, but also includes emission originating from the object itself, the polarization signatures would differ. Fluorescence from gases can generate polarization patterns distinct from those produced by pure dust scattering. However, this again necessitates an explanation for the emitting source and its nature. The polarization study, the inverted chemistry detected by Webb, and the depletion of carbon chains that paradoxically still permit a green luminescence. These observations collectively depict an object that defies expectations at every level. While it is possible to construct scenarios where each individual finding can be explained naturally, the aggregation of these anomalies in a single object requires the confluence of multiple improbable conditions. The comet would need to have formed in a very specific location to be carbon dioxide dominated. Subsequently, it would have to have been ejected at precisely the right moment to spend billions of years accumulating radiation damage in interstellar space. Then, during its journey, it would have coincidentally gathered dust with optical properties unlike anything we typically observe. Finally, it would have entered our solar system on a trajectory that brings it unusually close to multiple planets. The more specific the required conditions become, the less plausible the scenario. Adding to the enigma is the detection of cyanogen. Cyanogen is a compound of carbon and nitrogen. While not uncommon in comets, its presence is noteworthy because early observations detected it in 3I/Atlas, while simultaneously indicating a significant depletion of other carbon chain molecules, such as dicarbon and tricarbon. Luis Salazar Manzano at the University of Michigan analyzed spectra from the Kitt Peak Observatory. His team found evidence of cyanogen emission even before the comet was sufficiently close to the Sun to exhibit significant activity. This implies that cyanogen was present in a volatile form near the surface, readily released with minimal heating. However, cyanogen production in comets typically correlates with the presence of complex organic molecules and carbon chains. Discovering one without the others is unexpected, akin to finding smoke without fire. This suggests that the chemistry might not be following the pathways we assume, or that the molecules were not created through the standard processes of cometary formation and evolution, but rather introduced through mechanisms we have not yet considered. The chemical signature of 3I/Atlas appears almost designed to confound. Each measurement reveals properties that, in isolation, could be attributed to natural phenomena, but collectively, they push the boundaries of what natural processes are understood to produce. While chemists debate isotope ratios and spectroscopists analyze emission line profiles, Loeb has been undertaking a different calculation, one that renders the chemical questions secondary to a more immediate concern regarding the object's future actions. Chapter 8. The Precursor Probe Hypothesis. Loeb initiated his analysis with a straightforward geometric calculation. 3I/Atlas passed within 29 million kilometers of Mars on October 3rd, but this was not the closest it came to Mars' orbital path. The minimum orbit intersection distance, a metric indicating the closest proximity between one object's trajectory and another's complete orbital path, is a mere 2.7 million kilometers. While 2.7 million kilometers sounds like a vast distance, roughly 7 times the separation between Earth and the Moon, it is remarkably close in the context of orbital mechanics, particularly for an object traveling at 60 kilometers per second. This proximity suggests that a minor adjustment in velocity could bring the comet into direct collision with Mars. Loeb calculated the figures. A trajectory alteration of 10 to 15 kilometers per second, applied during September, would reduce that closest approach distance to zero. The comet would impact Mars, or, at the very least, pass within the planet's atmosphere. Natural comets do not undergo such substantial trajectory changes. The thrust generated by the outgassing of a natural comet might result in velocity changes of a few hundred meters per second over several months. Achieving 10 or 15 kilometers per second would necessitate either a catastrophic fragmentation event or active propulsion. However, this is where Loeb's attention was drawn. If 3I/Atlas is not a singular object but is accompanied by smaller components, these components do not need to match the main object's velocity. A mothership, releasing smaller probes, can impart significant relative velocities. The probes then separate, following slightly divergent trajectories. While the main object passes Mars at 29 million kilometers, a probe with the appropriate velocity vector could reach the planet. The Webb telescope measured the outflow velocity of gas from 3I/Atlas at 440 meters per second. This is the speed of material naturally vaporizing from the surface. However, if something were deliberately ejected, if a probe separated from the main body using mechanical force rather than thermal evaporation, it could achieve substantially higher speeds. A velocity of 10 kilometers per second is not unreasonable for a separation maneuver. It is well within the capabilities of conventional rocket propulsion. Even a rudimentary spring-loaded release mechanism could impart a few kilometers per second to a small object. Loeb therefore posed the question, if 3I/Atlas released precursor probes in September, could they have reached Mars? The answer is yes. Depending on the timing and direction of release, a probe could arrive at Mars anywhere from a few days to a few weeks after separation. Now, we must consider the practical implications. The HiRISE camera aboard the Mars Reconnaissance Orbiter was tasked with searching for 3I/Atlas. It was calibrated to detect an object 5 to 10 kilometers in diameter at a distance of 29 million kilometers. However, HiRISE is designed to image Mars' surface and can resolve features as small as 30 centimeters. If a smaller object, say 100 meters across, passed closer to Mars, even within a few 100,000 kilometers, HiRISE might have detected it. The critical caveat is that HiRISE was pointed at the expected location of the main comet. If a precursor probe originated from a different angle and followed a different path, it could have approached Mars unobserved by the spacecraft specifically tasked with tracking 3I/Atlas. The sky observations from the Perseverance rover become more pertinent in this context. Those images suggesting the presence of multiple objects, which were analyzed by Stephen Burns and others, were captured during a period when both the main comet and any potential companions could have been visible. If multiple fast-moving objects were indeed present in those images, and if they are not merely processing artifacts or background noise, we might be witnessing evidence of a dispersed system rather than a single, cohesive nucleus. Loeb extended his calculations to consider the period after perihelion, when the comet would swing around the Sun and emerge on the opposite side. The object would be obscured from Earth-based observation from late October through most of November. It reaches perihelion on October 29th, at a distance of 202 million kilometers from the Sun. During this closest approach, it would experience maximum solar heating, maximum radiation pressure, and maximum stress on any structural components. If it is a natural comet, this is when we would anticipate observing dramatic changes, increased activity, potential fragmentation, and a significant brightening of the coma as subsurface volatiles reach critical levels. If it is something else, something capable of maneuvering, perihelion presents a strategic opportunity. The gravitational assist from passing close to the Sun could be utilized to alter its trajectory. A minor velocity change at perihelion translates to significant positional changes months later. This is the principle by which spacecraft employ gravity assists to efficiently reach distant destinations. Loeb noted that with appropriate thrust applied at perihelion, 3I/Atlas could adjust its path to intercept Earth. The object will be traveling retrograde, opposite to the direction of planetary orbits. This geometry offers advantages for an intercept trajectory. It is not a chase, but a timed collision between two objects moving toward each other. A velocity shift of 30 to 40 kilometers per second during October could bring 3I/Atlas, or components thereof, to Earth between late December and early January. Is a 30 to 40 kilometer per second velocity achievable for a natural comet? Absolutely not. For a spacecraft with propulsion, it depends on the mass and the engine. Chemical rockets would struggle to achieve such velocities for an object as massive as 3I/Atlas. However, we are considering technology that has potentially traversed interstellar space, employing propulsion systems that we can barely comprehend. Loeb was careful in his phrasing. He did not assert that 3I/Atlas would maneuver toward Earth. He merely pointed out that the opportunity exists, that if the object possesses the capability, this is when and how it might utilize it. He then added a statement that was widely reported. If 3I/Atlas maneuvers toward Earth when it reappears from behind the Sun, financial markets may crash. Consider the implications of that statement. Beyond the immediate panic from news of an object heading towards our planet, it signifies a deeper realization, confirmation that we are dealing with technology, that something artificial has crossed interstellar space and is now approaching Earth. It implies we are not alone, and that whatever exists out there is aware of our presence. Markets crash on uncertainty, on fundamental shifts in our understanding of the world. The discovery of artificial interstellar technology would represent the most profound uncertainty in human history. Even if the object posed no direct threat and its intentions were benign, the knowledge that advanced civilizations exist and can reach our solar system would reshape every foundational assumption of our economic, political, and social systems. Loeb's statement was not fear-mongering. It was an acknowledgement that the implications extend far beyond the realm of astronomy. This is why the Mars observations are so critical, and why the silence from NASA and ESA feels significant. Right now, 3I/Atlas is approaching a juncture where, if it is to perform any unexpected actions, this is the window. We will not know what transpired until it emerges from solar occultation weeks from now, potentially having altered its course, potentially having released untrackable objects, or potentially having demonstrated capabilities that compel us to abandon the comfortable assumption that it is merely an unusual comet. Loeb refers to it as the Trojan horse, an innocent-seeming visitor that could harbor devastating consequences concealed within its ostensibly natural exterior. Chapter 9. Behind the Sun, the Danger Window. Loeb has devised a Loeb scale, a numerical ranking system from 0 to 10, quantifying the likelihood of an object being artificial rather than natural. A score of 0 signifies a definitively natural object, a chunk of ice and rock governed by predictable physics and exhibiting chemistry consistent with known processes. A score of 10 indicates a definitively artificial object, one displaying unambiguous technological signatures, maneuvering in ways requiring propulsion, or emitting signals or exhibiting structures inexplicable by natural means. Most celestial bodies, such as asteroids, comets, and meteoroids, all the debris adrift in space, score 0, as there is nothing about them that suggests technology. The initial interstellar visitor, designated oumuamua, has an assessed ranking between 3 and 5, fluctuating based on which observations are given prominence. Its peculiar form, its uncharacteristic acceleration independent of gravitational influence, and without apparent gas expulsion, and its erratic rotational movement. These characteristics elevated it beyond a baseline 0, but not sufficiently to confirm its artificial nature. The object referred to as 3I/Atlas currently holds a rating of 4. It is not rated at 0 because the anomalies observed are too numerous to dismiss. These include its trajectory aligning with planetary orbits, unexpected chemical compositions, the presence of nickel without accompanying iron, a forward-facing jet emanating from it with no discernible tail, and a significant discrepancy in its estimated mass. While any single one of these might be explained by natural phenomena, their collective presence substantially increases the probability of something beyond natural processes. However, it is not rated a 10 because definitive proof remains elusive. No detected radio transmissions, no observed deliberate maneuvers, and no photographic evidence of geometric construction have been recorded. The object continues to exhibit behaviors sufficiently akin to a comet that natural explanations, however improbable, cannot be entirely ruled out. A rating of 4 occupies a zone of uncertainty. While it is more probable than not that the object is natural, its peculiar characteristics prevent the hypothesis of artificial origin from being disregarded. Nevertheless, this classification could undergo a dramatic alteration depending on developments over the ensuing weeks. October 29th signifies perihelion, the point at which the comet achieves its closest proximity to the Sun, approximately 1.4 astronomical units, situated just within the orbital path of Mars. At this precise moment, from our terrestrial vantage point, it will be positioned directly behind the Sun. The Sun's apparent width in our sky spans roughly half a degree. 3E Atlas is slated to pass within this intense glare. Ground-based telescopes will be incapable of observing it. Orbital observatories such as Hubble and Webb are compelled to avoid aiming too close to the Sun to safeguard their sensitive apparatus. This renders us effectively blind to it. This period of obscured observation extends from late October through the majority of November. The precise dates are contingent on the viewing geometry and the comet's increasing brightness. Conservatively estimated, we will lose direct observational capability for a minimum of 3 weeks. These 3 weeks are critical, as they encompass the comet's peak exposure to solar heating, the maximum extent of any thermal stresses, and the period during which, if technological in nature, it possesses the privacy to execute its intended functions. Upon its reappearance, our focus will be on detecting any changes. The comet's luminosity serves as the primary indicator. Should the comet fragment or undergo a significant outburst, its brightness will increase markedly. Comets within our solar system occasionally experience brightness increases of several magnitudes during their closest approach to the Sun. If 3 Atlas replicates this phenomenon, it would strongly suggest the dominance of natural processes. Conversely, if its brightness remains unchanged or even diminishes, that would be a noteworthy observation. It might signify a more robust structure, less susceptible to thermal stress than typical comets. The object's trajectory represents the second key indicator. If it emerges on a path consistent with gravitational predictions, following the orbit calculated from pre-perihelion observations, this would bolster the natural explanation. However, any deviation, any alteration in velocity or direction not attributable to gravitational perturbations would rapidly elevate its classification on the anomaly scale. Spectroscopy will provide insights into compositional shifts. Will the surface chemistry be altered? Will new materials be exposed? Will the proportion of volatile compounds differ from our prior measurements? And what of its structure? Once 3 Atlas becomes visible again in early December, telescopes will immediately be tasked with photographing it. Will it appear unchanged? Will the forward-facing jet still be present? Will there be any indication of fragmentation or splitting? In parallel, Loeb is not merely engaged in theoretical calculations. He is actively observing the skies. The Galileo project operates 3 observatories, situated in Massachusetts, Pennsylvania, and Nevada. These facilities are outfitted with wide-field cameras, infrared sensors, and automated detection algorithms engineered to identify aerial phenomena that do not conform to conventional aircraft or known natural objects. The project's principal objective is the study of unidentified anomalous phenomena, commonly known as UAP, formerly referred to as UFOs. However, with 3 Atlas nearing its perihelion, Loeb has implemented a specialized monitoring protocol. Should the object be a mothership, and if it were to release smaller probes toward Earth as it traverses its solar orbit, these probes would be expected to arrive weeks or months later. The period between December and January becomes a critical window during which unexplained aerial activity might surge. The Galileo project's instruments will operate continuously, logging any unusual occurrences, identifying patterns, and searching for objects moving at speeds exceeding those of satellites, exhibiting flight characteristics beyond current aerospace capabilities, or appearing in numbers or at timings that correlate with 3 Atlas's perihelion passage. This may sound like science fiction, and in a sense, it is, as we are contemplating scenarios drawn from speculative narratives. However, the crucial distinction lies in our engagement with authentic data, precise calculations, and tangible objects that we can photograph and measure. If Loeb's hypotheses prove incorrect, and 3 Atlas is merely an anomalous comet with all its peculiarities explained by natural phenomena, the Galileo project will register no unusual findings. The object will re-emerge from behind the Sun, slightly brighter, potentially fragmented, and following its predicted trajectory. The nickel emissions will be attributed to exotic chemical processes. The observed trajectory alignment will be understood as a consequence of selection bias in which interstellar objects we happen to detect. Life will continue. But if he is correct, even partially, December will become one of the most pivotal months in human history. This significance will not stem from scenarios of invasion or hostile intent. Loeb is careful to avoid such framing. Even artificial constructs can be benign scientific probes dispatched by civilizations with no interest in interference. Rather, confirmation will alter everything. Every fundamental assumption about our position in the universe will be reevaluated. Every question regarding our solitude will be answered. Every decision concerning resource allocation and future planning will be made within a new context, one that acknowledges the feasibility of interstellar travel, the existence of other intelligences, and the profound reality that we are, in the most fundamental sense, not unique. The JUICE spacecraft, currently en route to Jupiter, is scheduled to observe 3 Atlas in late November. Between November 2nd and 25th, JUICE will direct its instruments toward the comet shortly after perihelion, as it emerges from the sun's glare and remains highly active. JUICE is equipped with cameras, spectrometers, and particle sensors. While it will be farther from the comet than Mars was, it benefits from observing during peak activity when the observable signatures are most pronounced. The data transmitted by JUICE will not reach Earth until February. The spacecraft is positioned on the far side of the Sun relative to Earth, utilizing its high-gain antenna as a thermal shield and communicating via a slower backup system. Consequently, we face months of waiting for these observations to be downloaded and processed. However, they are forthcoming and may reveal 3 Atlas's activities while obscured from Earth, its appearance at its most active moment, and whether any changes have occurred that necessitate our understanding. For the present, however, we are in darkness, both literally and figuratively. The object that has perplexed astronomers for months is about to vanish from view, concealed behind the overwhelming radiance of our star, presumably engaging in whatever activities it is designed for while unobserved. When it reappears, if it has undergone changes, if it exhibits any indication of deliberate action, Loeb's assessment will escalate from 4 to 5, possibly higher. The questions we have posed regarding its potential artificiality will then shift to inquiries about its intentions and our appropriate response. Chapter 10. What we are not being told. There exists a conventional protocol for how space agencies disseminate discoveries. Press releases are meticulously drafted. Scientists conduct interviews. Raw data is made accessible in public archives. Social media platforms share highlights. This entire process is designed to ensure transparency, foster public engagement, and justify the funding that enables these ambitious missions. When this established rhythm is disrupted, when scheduled observations are conducted but their results are not immediately published, or when inquiries are met with vague responses concerning ongoing analysis, it invariably draws attention. NASA's official registry for 3 Atlas lists the instruments that have observed or are slated to observe the object. This impressive roster includes Hubble, Webb, TESS, SWIFT, SPHEREx, Perseverance, Mars Reconnaissance Orbiter, Curiosity, Europa Clipper, Lucy, Psyche, Parker Solar Probe, Punch, SOHO, and ESA's JUICE. It represents a comprehensive deployment, with virtually every functioning space telescope and planetary mission directed toward this object at some juncture. Yet, the release of data does not align with the observation schedule. Webb's spectroscopic data from August was made available with remarkable speed, published as a preprint within weeks. Hubble's image from July was released to the public. SPHEREx findings concerning carbon dioxide emissions were also shared. However, once October commenced, the flow of information abruptly ceased. The observations made by Mars-based assets between October 1st and 7th should have been the most straightforward to disseminate. Mars orbiters routinely make their captured images public within a matter of days. The HiRISE website, which archives images from Mars, typically updates with new surface photographs every few days, and sometimes daily during periods of active observation campaigns. Nevertheless, no imagery from the 3 Atlas flyby has yet appeared. The European Space Agency operates under a distinct administrative framework compared to NASA. It possesses separate funding streams, oversight mechanisms, and public communication mandates. The simultaneous silence from both agencies regarding the same celestial target strongly suggests a coordinated effort. This coordination could signify collaboration, where scientists from both agencies are working together, agreeing to withhold statements until all data has been thoroughly analyzed. This is a logical approach for complex observations where preliminary findings might be susceptible to misinterpretation. Alternatively, coordination could imply consultation. This would occur if something unexpected has been discovered, necessitating discussions about the best way to present the findings, the appropriate context to provide, and the extent of additional verification required before public disclosure. The silence emanating from Simeon Schmaus, the astrophotographer who claimed to have observed early indications in the October 1st images, adds another layer of intrigue. Amateur observers typically share their findings with considerable eagerness. The astronomical community thrives on rapid discussion, crowdsourced verification, and collaborative analysis. When an individual becomes reticent after making a compelling claim, it usually points to one of two scenarios. Either an error has been identified, leading to embarrassment, or something significant has been discovered, prompting preparation for a more detailed presentation. Schmaus has neither retracted his observations nor posted any corrections. He has simply ceased to comment. Meanwhile, amateur astronomers continue their work with the data that is publicly accessible. The images posted by the Perseverance rover from those October nights remain available. Any individual with image processing software can download, stack, and examine these images for the presence of moving objects. Several independent analysts have now replicated Stephen Burns's finding of at least one rapidly moving object consistent with 3E Atlas. The ongoing debate centers on whether additional objects are discernible. Some analysts perceive them clearly, while others attribute the apparent extra lights to artifacts generated by stacking algorithms, cosmic ray impacts coincidentally appearing near the comet's path, or background asteroids. In the absence of high-resolution data from HiRISE and the ESA orbiters, and without official confirmation or denial, the question remains unresolved. What is evident is a discernible pattern. Official channels are constrained by rigorous review processes and institutional caution. Amateur observers are attempting to fill this informational void, albeit with varying degrees of scientific rigor and reliability. Meanwhile, the object itself continues to generate more questions than answers. Consider the significant unknowns that persist despite months of dedicated observation. The precise dimensions of the nucleus remain uncertain, with estimates ranging from less than 1 kilometer to over 10 kilometers, depending on assumptions regarding its albedo and whether the observations are primarily capturing the nucleus itself or an expanded dust coma. Its rotational rate is also unclear. Some observations suggest rapid spinning, while others fail to reveal a discernible periodic pattern. Understanding its rotation speed is crucial for assessing its structural integrity, determining if it's a single solid mass or a loosely aggregated collection of material. The source regions of its outgassing are also a mystery. Is material being expelled from discrete jets or from broad areas of the surface? Discrete jets would imply localized deposits of volatiles or specific structural features, whereas widespread emission would suggest a more uniform surface composition. The extent of any fragmentation is another key question. Has the nucleus fractured into multiple pieces? Are there companion fragments traveling alongside the main body, or is it structurally intact? These are fundamental inquiries that the Mars observations were expected to resolve. At a resolution of 30 kilometers, HiRISE should readily distinguish between a singular, compact object and a fragmented or multi-component system. Spectroscopic analysis from Mars Express and ExoMars should reveal regional compositional variations if they exist. The instruments functioned as intended, the observations were executed, and the data resides somewhere within agency archives. We simply are not privy to it. There are plausible, benign explanations. Data pipelines genuinely experiencing technical delays, scientists undertaking thorough analyses before releasing findings, and bureaucratic processes unrelated to the scientific content of the observations. There are also less benign explanations. Uncertainty regarding how to characterize unexpected discoveries, consultations concerning whether preliminary observations warrant broader discussion prior to formal publication, and institutional reluctance to make claims that could later necessitate embarrassing retractions. Finally, there are concerning explanations. The discovery of features that challenge established assumptions, evidence of structures or behaviors that defy natural categorization, and observations that, if released without adequate context, could incite the very speculation and public alarm that these agencies strive to prevent. We do not know which of these categories applies, and that is precisely the problem. The absence of information creates a void that is readily filled by conjecture. What can be stated with certainty is that the upcoming weeks hold immense significance. 3E Atlas will emerge from behind the Sun in late November or early December. Ground-based telescopes will immediately commence photographing it. Amateur astronomers will be observing diligently. Professional observatories will allocate observation time. If the object appears unchanged, if its trajectory aligns with predictions, and if its brightness and spectral signature remain consistent with previous measurements, the natural comet explanation will gain considerable strength. Conversely, if any changes are detected, evidence of maneuvering, structural modification, unexpected brightening, or novel compositional signatures, the hypothesis of artificial origin will be bolstered. JUICE will observe it in late November, during its peak post-perihelion activity. Europa Clipper, currently en route to Jupiter, may also conduct observations depending on orbital geometry and mission priorities. These spacecraft will observe the comet from perspectives and distances unavailable to Earth-based instruments. Their data will eventually be transmitted, processed, and will contribute to our understanding. However, eventually is not now. We are currently in a gap. A chasm exists between what has been observed and what has been disclosed. A divide separates amateur discoveries from official confirmation. There is a gulf between the questions we are posing and the answers that undoubtedly reside within data files to which we lack access. And while we remain in this state of waiting, 3 Atlas continues its journey, approaching the sun, intensifying its activity, and potentially undertaking actions that we will only become aware of weeks from now, when it reappears and we can discern what has changed. Thus, we find ourselves in a position of anticipation, observing an apparently empty sky where something extraordinary is currently hidden behind our sun. 3 Atlas is out there at this very moment, closer to our star than it has been in billions of years, absorbing immense quantities of solar energy, possibly fragmenting, possibly maneuvering, or potentially doing nothing more remarkable than comets have done since the solar system's inception. We have meticulously tracked its trajectory from the outer reaches of space, calculated its position when the WOW signal was received on Earth, measured the improbable ratios within its chemical composition, and documented the presence of metals that should not be there. We have mapped the tail that inexplicably points in the wrong direction. We have tallied the statistical improbabilities, accumulated the anomalies, and arrived at a juncture where certainty feels impossibly remote. Perhaps it is merely a comet, an unusual one, admittedly, but ultimately a natural object governed by natural laws. The anomalies will be resolved. The missing data will emerge and provide clarity. December will arrive, and the object will appear precisely as anticipated, slightly brighter, following its predicted path, reaffirming that the universe still adheres to discernible principles. Or perhaps we are witnessing an event that will fundamentally rewrite every assumption we hold about our place in the cosmos. Regardless, the forthcoming weeks will provide the answer, and we will be here to observe it. Thank you for remaining engaged with this narrative, for venturing into uncertainty with these inquiries, and for demonstrating a willingness to embrace mystery rather than demanding immediate, simple answers. If you have found this information valuable, please consider liking and subscribing to ensure you are present when the object reappears and we finally ascertain its identity. As always, this content is intended for educational and entertainment purposes. The scientific basis is real, and the observations are documented, but the interpretations remain speculative. We are exploring possibilities, not formulating definitive conclusions. We encourage you to conduct your own research and to question everything, including the information presented here. For now, 3 Atlas continues its silent transit behind the sun. December approaches. Amateur telescopes are prepared. Professional observatories have allocated observing time. The Galileo Project's instruments are actively recording data. And somewhere within the vast darkness, an object originating from another star pursues its solitary journey, unconcerned by our questions, our theories, or our hopes and fears regarding its potential significance. Sleep well, dream of distant constellations, and remember that the universe has perpetually surpassed our imaginings in its strangeness. Good night. Envision this scenario occurring at this very instant. At a distance of 620 light-years, a celestial body comparable in size to Jupiter is undergoing a process of consumption. This is not a gradual or delicate ingestion, but a violent one. 6 billion tons of gas and dust are being drawn in every single second into something that defies conventional astronomical classification, something that blurs the boundary between what we define as a planet and what we categorize as a star. Meanwhile, closer to home, on a world we have been studying for decades, a robotic probe, approximately the size of a car, has discovered within a rock what may indeed be the indelible mark of extraterrestrial life. Furthermore, within laboratories across the globe, scientists have just surmounted a barrier that has stood since the very inception of quantum computing, successfully constructing a machine capable of operating indefinitely. Theoretically speaking, this breakthrough unlocks possibilities that were previously projected to be decades away. However, what renders this particular week exceptionally peculiar is the confluence of these cosmic revelations with the discovery that our own biological systems harbor secrets we never suspected. Adipose tissue, the very fatty tissue we carry daily, has been identified as actively transmitting chemical signals directly to our brains. These signals may be instrumental in the formation of the very plaques that progressively impair our memories. And if we delve far back into the annals of time, to a period preceding all of this significance, before the emergence of humans, before the age of dinosaurs, even before the first tree ever took root, there existed a dominion that governed this planet for nearly a billion years. This kingdom was not composed of animals or plants, but of fungi, the enigmatic architects that fundamentally shaped the world we now inhabit. This is not a narrative of science fiction. This is the reality of this week. If you find yourself drawn into these profound mysteries, please indicate your engagement by hitting the like button and subscribing. Subsequently, share in the comments your location, the current time there, and which of these discoveries most profoundly challenges your understanding of reality. To further foster the growth of our community, consider sharing this content on X, Facebook, Reddit, or through your preferred messaging application. We are always grateful for your support. Chapter 1. The Leopard-Spotted Rock. On the 23rd day of July in the year 2024, a sophisticated machine, designated Perseverance, employed a drill bit to penetrate the surface of a rock on Mars. This particular rock had been assigned the designation Shava Falls, a name selected by the team on Earth who had been meticulously observing this stone for several months. Their reasons for focusing on this specific geological sample were well-founded. The rock was situated at the periphery of what was once a river valley, a channel that had historically conveyed rushing water into a crater that, more than 3.5 billion years ago, contained a lake. However, it was not solely its geographical context that prompted their decision to halt and investigate. The surface bore a distinct pattern. Dark, circular markings, encircled by lighter halos, were dispersed across the ruddy stone, reminiscent of a leopard's dappled coat. Such a sight was entirely unprecedented. A drill extracted a cylindrical core sample of rock, roughly the diameter of a pencil, which was then sealed within a protective tube for a potential return journey to Earth. Following this, the truly significant work commenced. The rover was equipped with sophisticated instruments capable of analyzing the rock's chemical composition without breaching the container. The revelations from these analyses sent profound reverberations through the scientific community, effects that continue to be felt today. The dark spots were found to comprise iron and phosphate. Nestled between the pale bands of calcium sulfate, traces of hematite, the very mineral responsible for Mars' characteristic red hue, appeared to be present. However, within this particular specimen, something had transformed the red pigment into a stark white. This type of chemical alteration releases iron and phosphate. Furthermore, these reactions are capable of supplying energy, specifically the kind that microorganisms utilize. On September 10, 2025, a scientific paper was published in the esteemed journal Nature. The researchers had dedicated an entire year to meticulously examining the collected data, conducting rigorous tests, and thoroughly verifying their findings. They detailed the existence of two specific minerals, vivianite and gragite, identified as iron phosphate and iron sulfide, respectively, on our own planet. These minerals typically form in oxygen-deficient environments where microbial life actively consumes organic matter, indicating conditions where life is sustained through chemical processes. The observed patterns aligned perfectly, and the chemical signatures were consistent. Every aspect of this rock strongly suggested a formation process that, on Earth, would unequivocally point to biological origins. The acting administrator of NASA convened a press conference. He announced that, after a year of thorough review, they had been unable to ascertain any alternative explanation. He conveyed to the world that this could very well represent the most compelling evidence of life ever discovered on Mars. While not definitive proof, it was the closest indication thus far obtained through their robotic endeavors. The media response was explosive. Headlines blared with reports of extraterrestrial microbes and the remnants of ancient Martian civilizations. The scientific community, however, adopted a more cautious stance, employing a term that, though sounding somewhat peculiar, carries immense scientific weight: potential biosignature. This designation refers to something that might have been produced by life, but requires further investigation before any definitive pronouncement can be made. This is precisely where the narrative takes a disheartening turn. The sample remains secured within the Perseverance rover's internal storage, sealed in its tube alongside 24 other samples acquired from various locations across Jezero crater. To definitively ascertain the origin of those distinctive leopard-like spots, scientists must retrieve the rock to Earth. They need to examine it using instruments far more sensitive than any that can currently be deployed on Mars, requiring advanced tools such as mass spectrometers and electron microscopes, equipment that typically fills entire laboratories. Fortunately, a program specifically designed to accomplish this very mission exists. It is known as Mars Sample Return. However, this ambitious undertaking is currently facing significant challenges. The projected expenditures have escalated dramatically, now estimated to be between $8 and $11 billion. The anticipated completion date has been pushed back to 2040 or even later. Subsequently, changes in political administrations, reorientations of governmental priorities, and budgetary restrictions have further complicated matters. As of the present moment, The Mars Sample Return Program exists in a state of suspended animation, neither officially terminated nor fully operational. Consequently, we possess a rock on Mars that potentially harbors evidence of ancient life, yet we lack a clear and viable pathway for its retrieval. Chapter 2. The celestial body that consumes like a star. Located 620 light-years from Earth, within the constellation known as Chameleon, exists an object that defies conventional astrophysical expectations. It bears a catalog designation rather than a common name, CHX 1107-7626, a sequence of alphanumeric characters utilized by astronomers to classify celestial discoveries. This object possesses a mass estimated to be between 5 and 10 times that of Jupiter, the undisputed giant of our solar system. This considerable mass firmly places it within the astronomical classification of a planet. However, it does not orbit a star. Instead, it drifts in solitary isolation through the interstellar void. It is one of what is believed to be trillions of rogue planets, aimlessly wandering the galaxy, detached and floating in the vast darkness between star systems. For an extended period, scientists presumed these wandering celestial bodies to be cold, inert, and dormant entities. The prevailing theories suggested they either formed around a star and were subsequently ejected due to gravitational disturbances, or they coalesced from gas clouds too small to initiate nuclear fusion, destined to remain perpetually dim and unremarkable. CHX 1107 has definitively disproven these assumptions. In the spring of 2025, astronomers directed the Very Large Telescope of the European Southern Observatory towards this enigmatic object. What they observed was a seemingly tranquil, nascent world, still enveloped by a disk of gas and dust, the residual material from its formation. This disk was slowly contributing to the planet's growth through a process known as accretion, where matter gradually accumulates on its surface, incrementally increasing its mass. This phenomenon is considered a normal aspect of planetary development. However, by August of that year, a dramatic shift occurred. The planet began to aggressively consume its surrounding disk. The process was not gradual but alarmingly violent, with the accretion rate skyrocketing to 8 times its previous speed within a mere matter of months. An astonishing 6 billion tons of material were pouring into this solitary world every single second, as it floated in the emptiness of space. To conceptualize this immense rate of consumption, imagine the entire mass of Mount Everest vanishing into this planet every few seconds. This voracious feeding frenzy persisted for a minimum of 2 months. Upon the publication of their findings on October 2, 2025, the object was still actively engaged in this process. The lead researcher, a scientist named Victor Almendrozabad, articulated a statement that perfectly encapsulates the profound strangeness of the discovery. People may think of planets as quiet and stable worlds, he explained. But with this discovery, we see that planetary mass objects freely floating in space can be exciting places. Exciting might very well be an understatement. The activity observed in CHX 1107 is a phenomenon that, until now, had only been witnessed in young stars and brown dwarfs, celestial bodies massive enough to exhibit complex magnetic activity. This represents the most significant accretion episode ever recorded for an object of planetary mass in the entirety of recorded astronomical observation. The situation becomes even more perplexing. The research team detected evidence of magnetic fields actively driving this influx of material. These powerful magnetic fields are channeling gas and dust towards the planet's surface, akin to invisible conduits traversing the cosmos. This is a process typically associated with stars, not planets. Stars possess the requisite mass and internal dynamics to generate potent magnetic fields. Planets, particularly rogue planets drifting in isolation, are not expected to exhibit such capabilities. Yet, here it is, demonstrably happening, observable and undeniable. The discovery also revealed the presence of water vapor in the planet's atmosphere during this period of intense activity, along with hydrocarbon molecules whose structures appeared to shift as the accretion intensified. These observations serve as indicators of heat and turbulence profoundly altering the chemistry of the surrounding disk. Scientists are now compelled to re-examine a question they believed had already been definitively answered: the origins of rogue planets. The two prevailing theories propose either ejection, where a planet forms around a star and is subsequently expelled through gravitational interactions, or direct collapse, where a cloud of interstellar gas collapses under its own gravity but never accumulates sufficient mass to ignite nuclear fusion. If ejection is the correct explanation, these planets should be cold and inert, their formative disks long since dissipated. However, CHX 1107 still possesses its disk and continues to grow, behaving in a manner consistent with formation in situ, condensing from a cloud much like a star would. only falling short of the critical mass required for fusion. This discovery blurs a previously distinct boundary. What truly differentiates the smallest stars from the largest planets? The defining characteristic has always been fusion, the ability of an object to sustain hydrogen burning within its core. But if objects within the planetary mass range can form like stars, grow like stars, and utilize magnetic fields like stars, then perhaps the dividing line is not as clear-cut as previously assumed. It suggests the existence of a spectrum, a gradient between planets and stars, with rogue worlds like CHX 1107 occupying a position somewhere in the middle, defying our established classifications. The researchers hypothesize that we are witnessing planetary formation unfolding in real time, observing a world actively constructing itself within the vast darkness between stars. Furthermore, this process is proving to be far more dynamic and violent than anyone had ever predicted. Chapter 3. The Unceasing Mechanism. Within a laboratory at Harvard University, a remarkable device is currently in operation, having been running for over 2 hours. This might not seem particularly extraordinary until one comprehends the nature of the machine itself. It is a quantum computer. For the entirety of the history of quantum computing, these devices have been plagued by a fundamental flaw. They cease functioning. This cessation is not due to an intentional shutdown, but rather because the quantum bits, or qubits, which are the foundational elements of their operation, simply degrade and vanish. In the parlance of physics, they decohere, meaning they lose their quantum properties and become inert. Early quantum computers could maintain their operational state for mere milliseconds. The most advanced machines managed to extend this duration to approximately 13 seconds before requiring a restart, a reset, and a renewed initiation of the computation. However, the research team at Harvard, under the leadership of Professor Misha Lukin, has engineered a fundamentally different system. In September of 2025, they published their groundbreaking findings in the journal Nature. Their quantum computer boasts 3,000 qubits and possesses the capability to operate continuously, without interruption or the need for restarts, for as long as they choose to supply it with power. Theoretically, its operational lifespan is indefinite. This achievement is not merely an incremental improvement. It represents a fundamental breakthrough that drastically redefines the capabilities of quantum computers. The core problem they have successfully addressed is as follows. Quantum computers function by precisely manipulating atoms or subatomic particles, maintaining them in incredibly delicate quantum states where they can simultaneously represent multiple values. This unique ability is the source of their immense power, enabling them to solve specific problems exponentially faster than conventional classical computers. However, these quantum states are inherently fragile. They necessitate extremely low temperatures, often approaching absolute zero, and require rigorous isolation from any external disturbances, such as vibrations, stray electromagnetic fields, or any other factor that could disrupt them. Despite these extensive protective measures, the qubits eventually falter. They leak information, their quantum states collapse, and the computation is abruptly terminated. The Harvard team dedicated 5 years to tackling this formidable challenge. They devised a novel method employing what they term an optical lattice conveyor belt, in conjunction with optical tweezers. These innovative tools utilize focused laser light to precisely capture individual atoms and manipulate their positions with extraordinary accuracy. The pivotal breakthrough involved discovering a method to replenish the qubits while the quantum computer remained operational. As qubits depart the system, new atoms are introduced to seamlessly replace them. The machine is capable of injecting 300,000 atoms per second, a rate that significantly surpasses the pace at which qubits are lost. Consequently, there is now no fundamental physical limitation to the duration of operation for these quantum computers. One of the researchers involved, Tout Wang, made a striking observation during an interview. There is still a way to go and scale from where we are now, he explained. But the roadmap is now clear based on the breakthrough experiments we've done here at Harvard. The phrase clear roadmap carries substantial weight in a field characterized by uncertainty and repeated delays in projected timelines. Another collaborator, Vladimir Gorshkov, a physicist from MIT, provided an even more specific outlook. He stated, "Before this, it was believed that continuously running quantum computers were at least 5 years away. Now it seems much closer, more on the horizon of 2 to 3 years." Consider the profound implications of this statement. Within the next 2 to 3 years, we may possess quantum computers that function analogously to the classical computers we utilize daily. Machines that do not cease operation after mere seconds, but remain continuously active, accumulating results, and capable of tackling complex problems requiring sustained computational effort. The ramifications of this advancement extend across numerous disciplines, including drug discovery, where quantum computers could simulate molecular interactions far beyond the reach of classical calculations. cryptography, potentially enabling the breaking of encryption schemes that secure global communications, artificial intelligence, where they could optimize neural networks in ways currently unimaginable, materials science, financial modeling, and climate prediction, essentially any domain where computational complexity surpasses the capabilities of traditional computing. However, there is another significant aspect to this unfolding story. Google also made a notable contribution to the quantum field recently, utilizing a 58-qubit quantum computer to create and observe what is termed a flow-K topologically ordered state. This is a novel phase of matter that had been theorized but never empirically observed. It exists only when a quantum system is subjected to rhythmic, periodic driving, thereby generating a non-equilibrium state that eludes capture by conventional physics. Researchers were able to witness exotic particles undergoing transformations in real time, thereby confirming theoretical predictions about the behavior of matter when subjected to conditions far from equilibrium. These are precisely the kinds of groundbreaking experiments that quantum computers facilitate, not merely accelerating calculations, but opening entirely new avenues for exploring the fundamental principles of physics itself. Chapter 4. The substance that communicates with your brain. Within your body, an astonishing process is currently underway, one that scientists have only recently begun to comprehend. Your adipose tissue, the fatty substance that cushions your organs and serves as an energy reservoir, is not a passive entity. It actively communicates, not through spoken language, of course, but via intricate chemical signals. These signals are transmitted in minuscule packages, enclosed within membranes, which travel throughout your bloodstream. These packages are identified as extracellular vesicles, and they carry a diverse cargo, including lipids, proteins, and genetic instructions. They possess the remarkable ability to permeate the walls of blood vessels and cross biological barriers that most molecules are unable to penetrate. Crucially, researchers have now definitively proven that some of these vesicles manage to reach your brain. A research team at Houston Methodist, led by scientist Stephen Wong, published their findings on October 3, 2025. They collected fat tissue samples from individuals who were both lean and obese. Subsequently, they isolated the vesicles released by these tissues and meticulously analyzed their contents. The lipid composition of the cargo was notably different. Specific fat molecules were found in greater abundance within the vesicles originating from obese individuals. These molecules include names such as lysophosphatidylcholine and sphingomyelin. In a subsequent phase of their research, the team performed a critical experiment. They exposed these vesicles to amyloid beta peptides, the proteins that form the characteristic sticky plaques found in the brains of Alzheimer's patients. The vesicles derived from obese tissue significantly accelerated the aggregation process of these proteins, clumping them together at a markedly faster rate. The lipids they carried acted as catalysts, hastening the very aggregation process believed to drive neurodegeneration. This finding transcends mere correlation. It elucidates a direct mechanism. The researchers have demonstrated that adipose tissue can transmit signals directly into the brain, and these signals can directly influence the speed at which the hallmark pathology of Alzheimer's disease develops. For years, obesity has been recognized as a risk factor for Alzheimer's, but the connection remained elusive, seemingly indirect, and mediated through factors like inflammation or insulin resistance. This groundbreaking study establishes a direct causal link. Adipose tissue releases vesicles. These vesicles traverse the blood-brain barrier, and within the brain, they deliver lipids that promote plaque formation. This outlines a clear pathway, a biological circuit that connects the body's energy storage system to one of the brain's most devastating diseases. Concurrently, another research group at Purdue University published related findings. Their focus was on cells within the brain itself, specifically microglia, the immune cells responsible for protecting neurons. In healthy brains, microglia continuously patrol, clearing cellular debris, combating infections, and maintaining overall homeostasis. However, in the brains of Alzheimer's patients, the microglia situated near amyloid plaques exhibit distinct alterations. They are swollen and engorged with lipid droplets, indicating fat accumulation within the cells themselves. The research team, headed by Professor Gareth Chopra, discovered that these lipid-laden microglia are severely impaired in their functional capacity. They are unable to effectively clear plaques, nor can they adequately protect neurons, essentially being incapacitated by their own excessive lipid burden. The team meticulously traced the biochemical pathway involved. When microglia encounter plaques and inflammatory signals, they begin to produce free fatty acids. Ordinarily, these would be utilized as fuel. However, in the diseased state, a critical malfunction occurs. An enzyme known as DGAT2 converts these free fatty acids into triglyceride, a stored form of fat. This conversion takes place in such copious quantities that the microglia become overwhelmed. Consequently, lipid droplets accumulate, rendering the cells immobile and incapable of performing their essential functions. Professor Chopra aptly described these accumulations as lipid plaques, a term that deliberately echoes the amyloid plaques that have traditionally garnered the majority of scientific attention, yet represents a distinct pathological entity. This lipid plaque pathology has remained largely overlooked for over a century. The most compelling aspect of this discovery lies in the researchers' successful intervention. They tested two specific molecules, one designed to inhibit DGAT2 and another intended to promote its degradation. The latter approach proved highly effective. It successfully reduced the accumulation of fat within the microglia, restored their capacity to engulf amyloid plaques, and resulted in improved markers of neuronal health in animal models of Alzheimer's disease. This suggests a novel therapeutic strategy, one that targets not the amyloid itself, but rather the lipid metabolism that cripples the brain's inherent defenses. This opens a new avenue of research, one that pharmaceutical companies have yet to fully explore, bridging the gap between Alzheimer's research and the study of lipid biology, metabolic disorders, and the significant proportion of the population living with obesity. Consider the far-reaching implications. For decades, Alzheimer's disease has been investigated primarily as a problem of protein misfolding, characterized by the accumulation of amyloid and tau tangles, leading to plaques and neuroinflammation. Numerous therapeutic agents have been developed with the aim of removing plaques or preventing their formation, yet most have ultimately proven unsuccessful. What if the reason for these failures lies in addressing the symptom rather than the underlying cause? What if the true driver of the disease is subtly hidden in plain sight, within the very fat that permeates our cells and transmits signals we have never before recognized? Chapter 5. The Kingdom That Prepared the World. Long before the emergence of forests, before the spread of grasses, and preceding the very first moss that anchored itself to a damp rock at the ocean's edge, something else was already present. It was not merely existing, but actively engaged in a vital process, breaking down stone, cycling essential nutrients, and establishing the fundamental chemical groundwork that would ultimately enable all subsequent life. We tend to conceptualize the origin of terrestrial life as beginning with plants, those verdant pioneers that colonized a seemingly barren surface. However, this surface was far from devoid of activity when the first plants arrived. For hundreds of millions of years, it had been meticulously prepared by a kingdom of organisms that often goes unnoticed by us, fungi. On October 1, 2025, researchers affiliated with the Okinawa Institute of Science and Technology published a seminal paper in Nature Ecology and Evolution. This publication, employing a novel combination of fossil evidence and an innovative technique involving horizontal gene transfer, the movement of genes between unrelated species, rather than solely through parent-to-child inheritance, effectively rewrites our understanding of the timeline of terrestrial life. They have traced the evolutionary origins of fungi back much further than previously conceived. The common ancestor of all currently living fungi is estimated to have existed between 1.4 billion and 900 million years ago. To provide context, land plants are believed to have appeared around 470 million years ago. This indicates that fungi underwent a period of diversification for potentially a billion years prior to the existence of the very first plant. This is not a minor adjustment to our understanding. It fundamentally alters the entire narrative of life's evolution. Complex multicellular life, organisms composed of numerous specialized cells working in concert, evolved independently on Earth precisely 5 times. These distinct lineages are animals, land plants, fungi, red algae, and brown algae. Each of these groups independently developed sophisticated mechanisms for cellular adhesion, intercellular communication, and the organization of cells into functional tissues. For the majority of these lineages, fossil records provide clear chronological markers. Animals, for instance, first appear in the fossil record approximately 600 million years ago, with notable impressions found in geological formations such as the Ediacaran. Red algae, potentially dating back as far as 1.6 billion years ago, are represented by fossils resembling ancient seaweed discovered in India. However, fungi, due to their soft, thread-like structures that decay rapidly, leave an exceedingly sparse fossil record, making the precise dating of their evolutionary timeline a significant challenge marked by missing pieces. The research team, led by scientist Gergely Saliki, ingeniously utilized horizontal gene transfers as temporal indicators. When a gene from one fungal lineage unexpectedly transfers to another, it establishes a temporal constraint. The ancestral lineage of the gene donor must predate the recipient lineage's descendant. By identifying 17 such documented gene transfers and integrating this information with the limited fossil evidence, the team was able to establish a remarkably precise timeline for fungal evolution. The picture that emerged was that of a kingdom that dominated Earth's continents for an almost incomprehensible span of time. Consider the profound implications of this revelation. For hundreds of millions of years, possibly approaching a full billion years, fungi constituted the most complex form of life on land. They were not entirely alone. Algae existed in the oceans and likely in shallow coastal environments, and bacteria formed extensive microbial mats. However, fungi possessed unique capabilities. They were actively engaged in chemical processes that no other life forms at the time could perform. They release compounds that disintegrate rock, freeing up phosphorus and other essential elements previously bound within minerals. These organisms form intricate webs, thread-like structures that link dispersed areas of soil, facilitating the transport of resources across landscapes. They engage in mutualistic relationships with other life forms, trading vital nutrients for sugars, thereby establishing beneficial partnerships for all involved. Researchers uncovered evidence indicating that some ancient fungi possessed the capability to degrade pectin, a key component of plant cell walls, as far back as 1 billion, 200 million to 800 million years ago. This suggests a historical interaction with algae, potentially aiding their survival in the challenging boundary between aquatic and terrestrial environments. By the time plants eventually emerged and began colonizing continents, they encountered a landscape already transformed by fungal activity. It was a world characterized by rudimentary soils, established nutrient cycles, and functioning chemical pathways. This perspective challenges the conventional narrative of pioneering plants. Flora did not conquer land independently. They inherited a realm that fungi had been shaping for millennia. Upon their arrival, plants rapidly formed alliances with fungi. We refer to these associations as mycorrhizae, and they are ubiquitous. 90% of terrestrial plants today host fungal partners within or around their root systems, exchanging sugars for essential minerals. It is highly probable, even certain, that plants would not have been able to colonize land without these symbiotic relationships. These partnerships likely trace their origins, both literally and evolutionarily, back to the period when fungi first began interacting with algae in the primordial shallows. Chapter 6. The Deceptive Condiment That Misled the World. In March of 2024, a modest clinical investigation was published in the journal BMJ Nutrition Prevention and Health. This study, originating from Lebanon, was conducted by investigators at Holy Spirit University of Catholic. It involved 120 young individuals, with an average age of 17, all of whom were either overweight or obese. The participants were segregated into 4 distinct cohorts. 3 of these groups consumed apple cider vinegar each morning, in quantities of 5, 10, or 15 milliliters, mixed with water and ingested prior to meals. The 4th cohort received a placebo, a simulated vinegar that visually and olfactorily resembled the real substance, but lacked the active component, acetic acid. The duration of the trial was 12 weeks. The outcomes, as reported in the published paper, were extraordinary. The individuals consuming the vinegar experienced weight loss, not insignificant, averaging between 6 and 8 kilograms, with the highest dosage group exhibiting the most substantial reductions. Their body mass index decreased, their waist and hip circumferences diminished, and their blood glucose levels, triglycerides, and cholesterol all showed improvement. The paper posited that apple cider vinegar decelerated gastric emptying, fostering a sense of satiety and curbing appetite. It presented visual representations and statistical analyses demonstrating clear and significant disparities between the vinegar-consuming groups and the placebo group. The journal publicized the study along with a press release. News organizations globally disseminated the information. Headlines heralded a straightforward, inexpensive remedy for a prevalent health concern. Apple cider vinegar, a staple in most pantries, was suddenly elevated to the status of a weight loss miracle. The study gained viral traction, leading to a proliferation of articles. Social media personalities began advocating for daily consumption of vinegar shots. The market for apple cider vinegar, already valued at over $1 billion, experienced a resurgence of interest. Individuals referenced the study in online forums, blog posts, and personal conversations. It carried the weight of peer-reviewed scientific validation, having been published in a journal affiliated with the BMJ Group, a reputable entity in medical publishing. However, a segment of researchers harbored skepticism from the outset. A gentleman named James Heathers, a consultant specializing in research integrity, commenced an examination of the paper shortly after its release. His findings caused him considerable concern. The age and body mass index distributions across the 4 participant groups were virtually identical. Statistically, this level of uniformity is improbable. When individuals are randomly assigned to experimental groups, some degree of variation is anticipated. However, The groups in this particular study appeared unusually congruent, as if they had been meticulously balanced rather than randomly allocated. Heathers published an analytical report in May of 2024, detailing what he characterized as implausible patterns within the data. He highlighted that if the reported results were accurate, apple cider vinegar would demonstrate a 50% greater efficacy than medications such as Ozempic, drugs that command thousands of dollars and necessitate a prescription. A single tablespoon of vinegar yielding superior outcomes compared to cutting-edge pharmaceutical interventions strained credulity. Other researchers voiced their apprehension through correspondence to the journal. The study had not undergone pre-registration, a prerequisite stipulated by BMJ Group editorial policy, designed to prevent the selective reporting of findings. The statistical methodologies employed were ambiguous. Attempts to replicate the analyses using the published data proved unsuccessful. The BMJ Group's content integrity team initiated an inquiry. They referred the paper to independent statisticians, soliciting their assessment of its reliability and their efforts to reproduce the reported outcomes. The statisticians were unable to do so. They identified numerous analytical discrepancies. They uncovered irregularities within the dataset that suggested the underlying raw data required independent verification. The numerical sums did not align. On September 23, 2025, 18 months following its initial publication, the journal formally retracted the paper. The retraction notice was unequivocal. The results were unreliable, multiple errors had been identified, and the data could not be substantiated. The authors, in their response, attributed the errors to honest mistakes and concurred with the decision to retract. Nevertheless, the reputational damage had already been inflicted. For a period of 18 months, the study had been cited as corroborating evidence. It appeared in systematic reviews and meta-analyses, which aggregate findings from numerous studies to derive broader conclusions. One such review, published shortly before the retraction, incorporated the invalid data, suggesting that apple cider vinegar might contribute to weight management. That particular review is now compromised, constructed upon a foundation that includes fabricated or severely flawed results. An editor at the BMJ Group, a woman named Helen McDonald, issued a public statement. While acknowledging the temptation to inform readers about a seemingly simple and beneficial weight loss aid, she declared, "At present, the results of the study are unreliable, and journalists and others should no longer reference or use the results of this study in any future reporting." However, how many articles remain accessible online without correction, still referencing the retracted research? How many individuals altered their behavior based on information that was subsequently proven false? Chapter 7. The Moon's Bifurcated Core. Our Moon possesses two distinct hemispheres, and they are not identical. This difference is readily apparent even with a modest telescope. The near side, the hemisphere perpetually facing Earth, is adorned with dark expanses known as maria. These are ancient plains of solidified lava that filled impact basins billions of years ago. The far side, concealed from our direct observation until spacecraft ventured behind it, presents a starkly different visage. It exhibits fewer maria and a greater density of impact craters, creating a landscape that appears older and less influenced by volcanic processes. For decades, this asymmetry has presented a puzzle to planetary scientists. Why would one hemisphere of the Moon differ so dramatically from the other? They are, after all, components of the same celestial body, formed from the same materials and shaped by the same cosmic history. Or so our understanding suggested. On October 3, 2025, researchers published an analysis of lunar samples retrieved from the far side by China's Chang'e 6 mission. These represent the inaugural samples ever obtained from this particular hemisphere, and their composition offers insights that challenge our previous notions about the Moon's internal structure. The rocks are rich in minerals typically derived from magma, molten rock that has cooled and crystallized. However, the chemical composition is anomalous. The samples contain a reduced concentration of heat-generating elements, specifically fewer radioactive isotopes of potassium, thorium, and uranium, compared to rocks originating from the near side. This distinction is significant because these elements are the primary source of internal heat within planetary bodies. Their decay over eons releases energy that can drive volcanic activity, leading to the melting of rock and its ascent to the surface. The researchers concluded that the far side originated from cooler magma, not merely slightly cooler, but substantially so. This implies that the Moon's interior is not uniform. It is not a straightforwardly layered sphere comprising a crust, mantle, and core arranged symmetrically. Asymmetry is ingrained in its deep structure, with compositional and thermal differences between the near and far sides dating back to the Moon's genesis. The prevailing hypothesis regarding the Moon's formation centers on a cataclysmic impact event. In the early stages of Earth's history, approximately 4.5 billion years ago, an object roughly the size of Mars collided with our planet. The impact was of such immense force that it vaporized rock, generating a disk of debris that entered orbit around Earth. This debris subsequently coalesced, drawn together by gravitational forces, ultimately forming the Moon. However, this process was neither smooth nor uniform. The Moon was likely in a molten state initially, a sphere of magma that cooled gradually over millions of years. As it cooled, denser minerals settled downwards, while lighter minerals floated upwards, establishing distinct layers. The recent findings indicate that this stratification occurred differently on the two hemispheres. It is plausible that the near side, facing Earth, absorbed greater heat from tidal forces originating from the gravitational pull of our significantly larger planet, which flexed and warmed its interior. Alternatively, the distribution of radioactive elements may have been uneven from the outset, concentrated more heavily on one side. Whatever the underlying cause, the result is a moon with a bifurcated internal structure. This observation carries implications beyond mere lunar geology, offering insights into the formation and evolution of rocky bodies. We often tend to assume symmetry when modeling planets and moons as spheres with uniform layers. However, if the Moon, a relatively small and uncomplicated body compared to a planet, can exhibit such profound internal asymmetry, it raises questions about other celestial bodies. Mars, for instance, displays hemispheres with vastly different characteristics. The northern lowlands are smooth and flat, while the southern highlands are ancient and heavily cratered. Could Mars also possess an asymmetric interior, with distinct thermal histories on each side? What about exoplanets, the thousands of worlds discovered orbiting other stars? We lack the ability to directly observe their interiors. Yet, if asymmetry is a common phenomenon, our existing models may be fundamentally flawed. The retrieved samples also revealed another significant finding. They confirmed that volcanic activity on the far side ceased earlier than on the near side. With a diminished supply of heat-generating elements, the far side could not sustain volcanism for as long. It became quiescent while the near side continued to erupt, filling basins with molten rock. This phenomenon creates a geological record, a timeline etched in rock, illustrating the decline of the Moon's internal heat budget over billions of years. By studying these samples, researchers can refine models that describe planetary cooling processes or the duration required for a celestial body to solidify internally and become geologically inert. Chapter 8. The ice concealing an ocean. Saturn boasts numerous moons, but one in particular consistently captures the attention of scientists, generates significant news coverage, and fuels speculation about the potential for extraterrestrial life, even within our own solar system. This is Enceladus, a diminutive world approximately 500 kilometers in diameter, encased in ice so luminous that it reflects nearly all incident sunlight. From a distance, it appears pristine, frozen, and devoid of activity. However, in 2005, the Cassini spacecraft flew sufficiently close to reveal the reality of its dynamic nature. Enceladus is far from dormant. It is actively erupting. From fissures located near its south pole, colossal plumes of water vapor and ice particles are propelled into space, creating geysers that ascend hundreds of kilometers above the surface. These are not intermittent events, but rather continuous, constant outflows, sustained by an entity concealed beneath the icy crust. A global ocean of liquid water, tens of kilometers deep, situated beneath an ice shell perhaps 20 to 30 kilometers thick. This ocean is maintained in its liquid state by tidal heating, a phenomenon analogous to the gravitational flexing that fuels the volcanic activity on Jupiter's moon, Io. Saturn's gravitational pull subjects Enceladus to rhythmic squeezing and stretching as it orbits, generating friction within the moon's interior, which produces heat and melts ice that, by all logical expectations, should remain frozen solid. Cassini traversed through these plumes, analyzing their composition with its onboard instruments. The discoveries were remarkable: water, naturally, but also salts, indicative of rock-water interactions occurring on the ocean floor. Silica particles, minute grains of silicon dioxide, form when hot water encounters rock at temperatures exceeding 90 degrees Celsius. Furthermore, organic molecules were detected, initially simple ones like methane and carbon dioxide, compounds containing carbon but not necessarily signifying life. Subsequent flybys revealed more complex molecules, including propane, ethane, and acetylene. Now, according to a fresh analysis of Cassini data published on October 2, 2025, even more intricate organic compounds have been identified, locked within the ice grains. The researchers re-examined data previously collected by Cassini, applying novel techniques and computational models to extract information that was not discernible in the initial studies. They identified organic compounds characterized by multiple carbon atoms, molecules that on Earth are typically associated with biological processes, although they can also arise from non-biological chemical reactions. The presence of these compounds does not constitute definitive proof of life, but it significantly strengthens the argument that the conditions within Enceladus Ocean could indeed support it. These conditions include liquid water, energy derived from tidal heating, organic molecules, and rocky surfaces conducive to chemical reactions. These are precisely the elements we seek when identifying potentially habitable environments. What makes Enceladus particularly compelling is that its ocean is not isolated. It maintains a direct connection to space through the aforementioned plumes. Any substances dissolved in the ocean water, any molecules, or even cells, if they exist, can be transported upwards through the fissures and ejected into space. This implies that a landing on Enceladus, followed by drilling through kilometers of ice to deploy instruments into a dark ocean, might not be necessary. Simply flying through the plumes and collecting samples could potentially allow for the detection of life without ever physically reaching the moon's surface. NASA and other space agencies have been actively discussing missions designed for this very purpose. These would involve spacecraft equipped to orbit Saturn, conduct repeated passes through the plumes, and analyze the ejected material with instruments far more sensitive than those carried by Cassini. However, a significant frustration persists. Similar to the challenges encountered with Mars sample return missions, these proposed Enceladus missions undergo development, study, and design phases, only to face delays. These setbacks are attributed to budgetary constraints, competing priorities, technical complexities, and shifts in political will. The earliest any dedicated Enceladus mission might be launched is projected for the mid to late 2030s, a decade or more into the future. In the interim, the body of evidence continues to grow. Each new analysis of Cassini data unveils greater complexity and further indications that Enceladus is not merely habitable, but potentially inhabited. We have a world possessing an ocean, an energy source, and organic chemistry, all expelling its secrets directly into space for our sampling, and yet we are compelled to wait. Saturn harbors other moons with subsurface oceans. Titan, a colossal moon with a dense atmosphere and methane lakes, almost certainly possesses a water ocean deep beneath its icy shell. Jupiter's moon Europa harbors an ocean that may contain twice the volume of all of Earth's oceans combined. Ganymede and Callisto are also believed to harbor oceans. Our solar system, it transpires, is not arid but rather replete with liquid water, featuring numerous hidden seas locked beneath layers of ice. These oceans have existed for billions of years, remaining stable, shielded from radiation, and potentially teeming with forms of life that we have yet to comprehend. Chapter 9. The predator preceding the blood. When one considers a leech, the typical mental image is likely that of an unpleasant creature, a dark, slug-like organism that attaches to skin, feeds on blood, and leaves a wound that continues to bleed due to anticoagulants present in its saliva. Leeches are parasites, organisms that sustain themselves by deriving resources from others. They possess soft bodies, are generally not endearing, and are rarely preserved in the fossil record due to the scarcity of soft tissue preservation. However, on October 2, 2025, researchers announced the discovery of a leech fossil that fundamentally alters our understanding of these creatures. This fossil dates back 430 million years, predating any previously identified evidence of leeches by 200 million years. The fossil originates from a geological formation renowned for its exceptional preservation, capturing not only the outline of the animal, but also the structural details of its body segments, the morphology of its head, and even subtle indications of its internal anatomy. What has astonished paleontologists is not solely its age, but rather what the fossil reveals about the nature of leeches prior to their evolution into parasitic forms. This ancient leech was not a blood feeder. It was a hunter, an active predator equipped with jaws and a body adapted for locomotion in open water. It inhabited the marine environment, rather than the freshwater ponds or terrestrial habitats where modern leeches are typically found. In every respect, it represented a distinct kind of animal from the leeches we know today. Modern leeches belong to the group Hirudinida, within the broader phylum Annelida, the segmented worms. They are closely related to earthworms and marine bristleworms, all sharing a body plan constructed from repeating segments. However, leeches have lost the bristles and the rigid chetae that other annelids use for traction. Instead, they have evolved suckers, one at each extremity of the body, and a muscular, flexible form that enables them to move along surfaces with a creeping motion or swim through undulatory movements. Most significantly, many leeches have developed specialized mouthparts designed for piercing skin and consuming blood, a lifestyle that necessitates biochemical adaptations, such as enzymes to prevent clotting and stealth mechanisms to evade detection, all integrated into their saliva. transforming a simple bite into a sophisticated parasitic strategy. Yet, for 130 million years ago, none of these adaptations had yet materialized. The fossil leech possessed a different physique, longer, more streamlined, built for speed rather than attachment. Its jaws were sharp, but not adapted for puncturing skin. Instead, they were designed for grasping, for securely holding prey, and for dismembering small invertebrates in the water column. This creature was a carnivore, a marine predator that actively swam and pursued other animals. The researchers who studied the fossil, publishing their findings in a peer-reviewed journal, described it as a portal into a vanished world, a period when leeches were not the despised parasites we associate them with, but rather legitimate hunters within marine ecosystems. This discovery compels a re-evaluation of leech evolution. The parasitic lifestyle and blood-feeding behavior emerged at a later stage. It was not the ancestral condition. Sometime during the intervening millions of years, a lineage of hunting leeches shifted its strategy. Perhaps they began scavenging on dead animals, feeding on existing wounds. Or perhaps they transitioned to opportunistically feeding on live animals, consuming small quantities of blood when the opportunity arose. Over time, these opportunistic feeders evolved into specialists, refining their mouthparts, saliva, and behavior until they became the obligate parasites we observe today. However, the fossil unequivocally demonstrates that leeches originated as something entirely different. This raises a pertinent question. Do hunting leeches still exist? Are there undiscovered lineages that never underwent the transition to parasitism? The ocean is vast and inadequately explored. We possess more detailed maps of Mars' surface than of the deep sea floor. New species are continuously discovered, including peculiar worms and bizarre invertebrates that defy existing taxonomic classifications. It is entirely plausible that somewhere in the abyssal depths, within a trench or canyon we have yet to investigate, reside leeches that still hunt, that still live as their ancestors did 430 million years ago. The fossil serves as a potent reminder that evolution is not a linear progression, nor a deterministic march towards increased complexity or perfection. It is a branching tree where lineages diverge, experiment, with some succeeding and others becoming extinct. Each adapts to its prevailing environment and available opportunities. Chapter 10. How Words Reshape Reality. There exists a form of manipulation so subtle, so insidious, that the recipient remains unaware of its occurrence until their grasp on reality has already been significantly compromised. This phenomenon is known as gaslighting. The term originates from a theatrical production staged in 1938, which was later adapted into a cinematic feature. In this narrative, a husband deliberately maneuvers his wife into doubting her own sensory input, her own recollection of events, and her own mental stability. He would subtly reduce the illumination in their dwelling and then assert that no alteration had occurred. He would conceal personal belongings and then claim she had misplaced them. He would actively dispute her accounts of past occurrences until she lost all faith in her own judgment. While the play itself was a work of fiction, the behavior it portrayed is a profoundly real and damaging phenomenon. On the 2nd of October, 2025, academics from McGill University and the University of Toronto released their findings, which redefine gaslighting not as mere deceit, but rather as a cognitive process deeply intertwined with how our neural networks process conflicting data. This study, disseminated within a peer-reviewed neuroscience periodical, characterizes gaslighting as a corrupted form of associative learning, wherein persistent exposure to fabricated information from a trusted originator can supersede direct sensory perception. They elucidate that your brain is in a perpetual state of constructing a global model, a mental framework that anticipates future occurrences. This model undergoes continuous refinement based on two distinct informational conduits: what you directly apprehend through your senses and what you glean from other individuals, particularly those you hold in esteem. Under typical conditions, these two streams of input harmonize. You observe a crimson apple, and an individual informs you that it is crimson. The information aligns, reinforcing your mental model. However, gaslighting introduces a dissonance. You perceive a crimson apple, yet an individual you trust declares it to be emerald. At this juncture, your brain encounters a dilemma. It must ascertain which informational source warrants greater credence. If the individual contradicting you is someone upon whom you rely, someone who has historically proven dependable, or someone possessing social or emotional influence over you, your brain might elect to prioritize their assertion over your own visual evidence. This is not a conscious deliberation, nor a calculated choice, but rather an automatic calibration within the learning algorithm your brain employs to navigate existence. The researchers employed advanced brain imaging techniques and behavioral experiments to scrutinize this mechanism. They presented participants with a sequence of visual stimuli, followed by input from confederates, individuals collaborating with the research team who provided inaccurate descriptions of the image's content. These confederates were presented as authorities, individuals possessing specialized insight, thereby cultivating an environment where their pronouncements carried significant weight. Across multiple experimental iterations, the participants began to question their own perceptions. When subsequently asked to recall the images they had viewed, they increasingly reported the fabricated information disseminated by the confederates, rather than what they had genuinely observed. Neural scans revealed heightened activity in brain regions associated with conflict resolution and memory reconsolidation, areas that become engaged when the brain is actively reprocessing stored data to integrate novel information. This is not indicative of intellectual deficiency or a lack of fortitude. Rather, it is the brain functioning as it was evolutionarily designed to do, which is to acquire knowledge from others. Humans are inherently social beings. Our survival depends on the exchange of information and the reliance on the collective wisdom of our communities. If every member of your cohort informs you that a particular flora is noxious, you are spared the necessity of first-hand experience to confirm this. You place trust in their collective knowledge, and that trust safeguards your well-being. However, this very mechanism, this system of social learning, can be perverted and exploited. If an individual wielding authority over you consistently refutes your lived experiences, your brain may begin to accord precedence to their interpretation of events over your personal recollections. You commence to harbor doubts about yourself. You scrutinize your own perceptions. You experience bewilderment and disorientation, as though you are losing your grasp on objective reality. In a metaphorical sense, this is precisely what is occurring. Your internal construct of the world is being systematically rewritten by the pronouncements of another. The ramifications of this phenomenon are profound. Gaslighting transcends the realm of abstract psychological maltreatment. It constitutes a direct interference with neural processes and exploitation of the fundamental ways in which the brain acquires and retains information. The researchers underscore that comprehending this underlying mechanism represents the crucial initial phase in developing defenses against it. If you are aware of your brain's susceptibility to authoritative refutations, you can implement protective measures. You can maintain records, document observations, capture photographic evidence, and establish external reference points for your memory that cannot be readily undermined by another's persistent assertions. You can also seek corroboration from a multiplicity of individuals, verifying your perceptions against those of people external to the manipulative dynamic.